Hello there, and welcome to Sleepy Cosmic Lens, where we take the largest questions in the universe, lower the lights a little, and examine them without rushing. Tonight, we are going to ask a question that sounds simple at first, but becomes stranger the longer you sit with it. How much force would it take to break space-time? Just imagine that for a moment. What would that even look like? A crack running through the room? The stars going out, one by one? Or would it be something so utterly profound that it wouldn't look like anything at all? This is a journey into the heart of physics, where we'll explore the life and death of stars, the crushing gravity of black holes, the ripples of gravitational waves, and the very limits of what we can know. We're going to ask if reality itself is fragile or if it's as solid as eternity. So, settle in. Let's find out. That is quite a dramatic question for such a quiet evening. It sounds as though space-time might be a sheet of glass, waiting for the right cosmic hammer, or an old floorboard that could finally give way if a sufficiently heavy star stepped on it. Physics, as usual, is not quite that straightforward. Space-time is not a material in the ordinary sense. You cannot hold a piece of it in your hand, fold it into a drawer, or accidentally damage it while moving furniture. Still, the universe contains objects and events so extreme that the structure of space and time can be bent, stretched, squeezed, and pushed into conditions where our best theories stop giving clear answers. Before we move any farther, take a moment to notice where you're listening from tonight. Perhaps you're in a bedroom with the curtains drawn, on a sofa with a lamp still on, or somewhere much less restful, such as an airport chair designed by someone who clearly disliked the human spine. What part of the world are you in, and what time is it there? While you settle in, consider something else. Have you ever felt the surface beneath you flex slightly under weight? A mattress sinking when you lie down? A wooden bridge shifting under footsteps? Or a sofa cushion giving up all resistance after years of loyal service? Those are ordinary materials responding to pressure. The question before us is whether reality itself can do something similar, and what might happen if the pressure becomes too great. If you find these slow journeys through science relaxing, interesting, or useful for giving your thoughts somewhere calm to go, you can leave a like and subscribe to the channel. It helps more listeners find this small corner of physics, especially those who enjoy learning about black holes at an hour when sensible people are asleep. For now, there is nothing you need to remember, calculate, or solve. Just follow the ideas at an easy pace. The phrase break space-time creates an immediate picture, but it can also be misleading. Breaking usually means that something once connected becomes separated. A rope snaps, a window cracks, a biscuit breaks in half, often when you are trying to dip it into tea with more confidence than the biscuit deserved. In each case, the object is made of smaller pieces held together by forces. Apply enough stress, and those bonds fail. Space-time does not appear to be built in quite the same way, at least not at scales we can observe directly. It is the framework in which positions, distances, durations, and motion have meaning. Asking what could break it is a little like asking what could tear the idea of distance or put a crack through the passage of a second. Yet, physicists do use language that comes close. They speak about singularities where known equations produce quantities that become unbounded. They study horizons that divide regions of the universe in ways no ordinary wall could manage. They investigate violent collisions that send disturbances across billions of light years. They also consider whether space-time might have a smallest possible structure, and whether that structure could become unstable under extreme conditions. None of this means the universe is about to split open beside your bed. It means the word break has several possible meanings, and each one leads us toward a different edge of physics. One meaning would be to curve space-time so strongly that every possible path nearby is dragged inward. This is what happens around a black hole. A black hole is not a hole punched through a background sheet. It is a region where matter or energy has changed the geometry around it so severely that, beyond a certain boundary, light can no longer escape to the outside universe. That boundary is called the event horizon. Nothing necessarily snaps there. A traveler falling through a very large event horizon might not notice a sudden surface or barrier at the moment of crossing. The real trouble lies deeper in, where the theory points toward a singularity and stops describing events in a normal, complete way. Another meaning would be to produce a tier or tunnel connecting places that are normally far apart. Science fiction often presents this as a rip in the fabric of space. Physics has mathematical ideas that resemble tunnels, including wormholes. But a mathematical possibility is not the same as a stable object that can be built, visited, or used for a weekend trip. A wormhole would not necessarily be broken space-time. It could instead be an unusual arrangement of space-time, rather like a road that takes a shortcut through a mountain instead of damaging the countryside. The difficulty is that keeping such a shortcut open may require forms of matter or energy that we do not know how to gather in useful amounts, assuming nature permits them in the necessary form at all. A third meaning is more serious. Space-time might be considered broken when the laws used to describe it can no longer predict what happens next. Physics depends on being able to connect earlier conditions with later outcomes. The prediction does not need to be easy, and it does not always need to be certain, but the theory must at least tell us what kinds of outcomes are allowed. If a region appears where the equations lose that ability, then something fundamental has gone wrong. Perhaps space-time itself has reached a genuine limit. Perhaps the theory is incomplete, or perhaps the question has been framed in the wrong way. That distinction will matter throughout our journey. When a map ends at the edge of the known territory, it does not mean the land ends there. It may only mean that no one has drawn the next section yet. General relativity, our leading theory of gravity, has been remarkably successful. It explains the motion of planets, the bending of light, the behavior of clocks and gravitational fields, and the waves produced when massive objects accelerate. It has passed many difficult tests. Even so, its own mathematics leads toward places where the theory appears to fail. Those places are not proof that space-time literally breaks. They are signs that our current map may be missing a deeper description. To understand why force is not quite the right word, imagine pressing your hand into a cushion. The harder you push, the deeper the surface bends. It feels natural to think of gravity in the same way. Place more mass in one region and space-time bends more. This comparison is useful, but it has limits. A cushion bends into the space around it. Space-time does not need some larger room outside the universe in order to curve. Its curvature is measured through relationships within space-time itself. Clocks run at different rates. Paths that would otherwise remain parallel can move together. Light follows routes that appear bent. The geometry changes, and objects respond to that geometry. Force in everyday life is something that pushes or pulls. Gravity in general relativity is described differently. A freely falling object is not being dragged by an invisible rope. It is following the straightest available path through curved space-time. That path may look curved when we describe it using ordinary coordinates, but from the object's local point of view, it is simply moving naturally. This means our central question needs a small adjustment. Instead of asking only how much force would break space-time, we should ask how much energy, mass, pressure, or concentration would be required to make the geometry reach an extreme condition. Concentration is the important part. A large amount of mass spread over a huge region may produce gentle curvature. The same mass compressed into a much smaller region can produce something far more intense. Earth curves space-time, but not enough to trap light. The sun curves it more strongly, yet sunlight still escapes without difficulty. Compress enough mass within a sufficiently small boundary, and an event horizon can form. It is not simply the amount of material that matters. It is how tightly that material is packed. This is why a black hole can form from a collapsing star. A massive star spends much of its life balancing two tendencies. Gravity pulls inward while pressure produced by heat and nuclear processes pushes outward. When the star runs out of fuel for the reactions supporting its core, that balance can fail. The outer layers may explode away while the central region collapses. In some cases, no known pressure can stop the collapse. Matter is compressed, curvature grows, and a black hole forms. Does that count as space-time breaking? Not in the ordinary region outside the black hole. The geometry there can be described very well. We can calculate orbits, predict how light bends, and model how matter heats as it falls inward. The event horizon is also a regular feature in the mathematics when described carefully. The likely breakdown comes at the center, or at least at the place classical relativity identifies as the center. There, density and curvature are driven beyond the theory's ability to provide a physical answer. The word beyond is useful here. It prevents us from pretending we know more than we do. When a theory produces an infinite result, nature is not always announcing that an actual infinity exists. Sometimes the theory is telling us that it has been extended past the conditions where it can be trusted. An old navigation chart might mark a dangerous area with vague shapes because the survey was incomplete. That does not mean the ocean becomes mathematically infinite at that point. It means better measurements and a better model are needed. At the center of a black hole, better measurements are not easy to arrange. Information from inside the event horizon cannot travel outward in the usual way. No probe can descend, take readings, and send a cheerful report back to the laboratory. We must rely on theory, indirect evidence, and consistency with everything we can observe outside. This leaves room for several possibilities. A deeper theory might replace the singularity with an extremely dense but finite state. Space-time might become granular at very small scales. The familiar ideas of location and duration might stop applying, or the interior might contain structures that are not captured by our current concepts at all. There is another route toward extreme space-time that does not begin with a single collapsing star. Two black holes can orbit one another, lose energy through gravitational waves, and eventually merge. During the final moments, the geometry changes rapidly. The black holes combine, the surrounding space-time rings like a disturbed bell, and waves travel outward at the speed of light. The event is violent enough to release an enormous amount of energy in a very short time. Yet space-time does not shatter like glass. It carries the disturbance away. That alone tells us something important. Space-time is not fragile in the ordinary sense. It can handle events that make every human explosion look insignificant. It can be curved by stars, shaken by collisions, and stretched by the expansion of the universe. Gravitational waves cross enormous distances while becoming weaker, and detectors on Earth can measure the tiny changes they produce. Reality seems capable of transmitting a remarkable amount of disturbance without developing a loose edge or dropping pieces behind the sofa. Still, there may be limits at sufficiently small scales and high energies. General relativity must somehow meet quantum physics. General relativity treats space-time as a smooth geometry. Quantum physics describes nature in terms of fields, probabilities, and discrete interactions. Each theory works extremely well in its own domain. The problem appears when both are needed at once, such as near the classical center of a black hole or during the earliest known stage of the universe. Physicists expect a theory of quantum gravity to give a more complete account, but there is no single experimentally confirmed theory that settles the matter. Several approaches offer different pictures. Some suggest that space-time is made from tiny units or networks. Others describe fundamental objects whose behavior gives rise to the dimensions we experience. There are also proposals in which space-time is not fundamental at all but emerges from deeper relationships, much as temperature emerges from the collective motion of many particles. If space-time is emergent, breaking it might resemble disrupting the underlying system so completely that the large-scale description no longer applies. A wave can break on a shore even though water itself does not break. A traffic jam can dissolve even though the road remains. A solid can melt, changing its large-scale behavior while its basic particles continue to exist. In a similar way, what we call space-time might cease to behave smoothly without reality itself becoming nothing. This is one reason the phrase "how much force" needs careful handling. There may not be a single value, a single cosmic limit, or one final push that causes space-time to fail everywhere. Different kinds of extreme conditions may produce different kinds of breakdown. Concentrated mass may create a horizon. Rapid acceleration may generate powerful gravitational waves. Enormous energy packed into a tiny region may require quantum gravity. Certain theoretical arrangements might alter causal structure, changing which events can influence which others. The result depends not only on how much energy is present, but on where it is, how it moves, how it is distributed, and what geometry already surrounds it. The scale of these conditions is difficult to picture because human experience takes place in a gentle gravitational environment. Even the gravity that holds you to Earth is weak compared with the fields near neutron stars and black holes. We notice gravity constantly because it acts over long distances and because the entire planet participates. Yet, you can lift a small object from the floor using the electromagnetic forces in your muscles. overcoming the gravitational pull of the whole Earth on that object. Gravity is persistent, but at ordinary scales it is surprisingly weak. Near compact objects, the situation changes. A neutron star can contain more mass than the Sun compressed into a sphere roughly the size of a city. Its surface gravity is immense. Matter there is forced into states impossible to reproduce in bulk on Earth. Move closer to a black hole, and differences in gravity from one point to another can become severe. These differences are called tidal effects. They can stretch an object in one direction and squeeze it in another. For a small black hole, those effects near the horizon could be fatal long before any traveler had time to admire the view. Around a supermassive black hole, the horizon can be crossed where local tidal effects are much milder, though the journey farther inward would still end badly. Tidal effects give us another possible meaning of breaking. Space-time may remain mathematically smooth while objects inside it are pulled apart. A planet, star, or unfortunate spacecraft can be disrupted because neighboring parts are forced onto increasingly different paths. The object breaks, not space-time. This is an easy distinction to lose in dramatic descriptions. When we say gravity tears something apart, it does not follow that gravity has torn the underlying geometry. The universe also provides examples of expansion rather than collapse. On very large scales, distances between unbound galaxies increase as space expands. In the early universe, expansion may have gone through a brief period of extraordinary acceleration. Some speculative models consider futures in which expansion becomes so intense that galaxies, solar systems, planets, and eventually smaller structures are pulled apart. This idea is often called a big rip. It depends on the nature of dark energy, which remains uncertain. Even in that scenario, saying space-time breaks would be a shorthand. The geometry would evolve in a way that destroys bound structures, while the deeper meaning of the final state would depend on the correct physical theory. There are more exotic possibilities in theoretical physics. Cosmic strings, if they exist, could create unusual distortions. Collisions at energies far beyond current machines might probe the smallest meaningful scales. Certain solutions of relativity allow closed paths through time, although whether nature permits the required conditions is another question. The common theme is that the equations allow us to explore situations far outside ordinary experience, but they do not always guarantee that those situations can form in the real universe. A useful scientific habit is to separate three questions. Can the mathematics describe it? Can nature produce it? Can we observe evidence for it? Those questions often have different answers. A model may allow a space-time tunnel while realistic matter cannot keep it open. A theory may predict a singularity while a future quantum theory removes it. An event may occur behind a horizon while no direct signal can escape. Keeping these distinctions clear will help us avoid turning every unusual equation into a claim that reality has developed a crack. For the moment, we can already give a cautious answer to the question we began with. There is no known ordinary force that simply snaps space-time. Extreme mass and energy can curve it dramatically. Collapse can produce black holes. Collisions can send strong ripples through the universe. The classical description can reach singularities where it stops being complete. At very small scales, space-time may lose the smooth character we assume in everyday physics, but none of these is exactly like breaking a physical object. The more useful question is what space-time is capable of enduring before our familiar description fails. That moves us away from the image of a cosmic hammer and toward the actual physics. We need to understand what bending means, how curvature is measured without treating space-time as a substance, why mass and energy alter geometry, and how much distortion can occur before horizons, singularities, or quantum effects enter the picture. So keep the image of the cushion if it helps, but do not trust it too completely. Space-time is not a rubber sheet, and the universe is not sitting on a table beneath it. The comparison is a doorway, not the room itself. To move closer to an answer, we first need to look at what physicists really mean when they say that space-time bends, because only then can we decide whether bending can become breaking. That question sounds as though it should have a simple answer. If space-time bends, then surely it must bend in the same way as a sheet, a branch, or the cushion we mentioned a moment ago. Put something heavy on it, watch it sag, and there you are, gravity explained. This is the picture many of us first encounter, and it is useful as long as we remember that it is only a picture. The real meaning of curved spacetime is more precise, more practical, and in some ways much stranger. Begin with something familiar. Imagine walking across a flat field. If you choose a direction and continue in a straight line, you expect your path to remain straight. Two people starting side by side and walking in exactly the same direction should stay the same distance apart, assuming neither of them is distracted by a particularly confident goose. This is how flat geometry behaves. The rules are simple, and they match the sort of geometry taught in school. Straight lines remain straight. Parallel paths remain parallel. The shortest route between two nearby points is the direct one. Now imagine doing the same thing on the surface of Earth. The ground may feel flat beneath your feet, but the planet as a whole is curved. Two travelers can begin at different places on the equator. Both walk directly north and eventually meet near the North Pole. Neither person turned toward the other. Each followed the straightest route available on the curved surface. Their paths came together because the surface beneath them was not flat. That example shows what curvature can do without requiring a visible bend. A small insect walking on a large ball might never see the ball from outside, yet it could still discover the curvature by making measurements. It could draw large triangles and notice that the angles do not behave as they would on a flat page. It could send two companions along paths that begin parallel and see those paths converge. It would not need to step into a higher dimension and admire the ball from above. The geometry could be understood from within. Spacetime curvature works in a related way. We do not need to imagine the universe bending into some larger external space. We look at how objects move, how light travels, how clocks run, and how distances behave. When those relationships differ from what flat spacetime would predict, we say the geometry is curved. The word spacetime joins two ideas that once seemed separate. Space tells us where an event happens. Time tells us when it happens. In ordinary life, separating them feels natural. You might say a meeting is in the kitchen and begins at 8 in the evening. One part of the description gives the place and the other gives the time. Relativity shows that these parts belong to a single structure. Different observers can disagree about distances and durations, but they agree on the deeper space-time relationship between events. An event in physics is simply something that happens at a particular place and time. A light switch is flipped on, a star explodes, a spoon falls from the table after being placed slightly too close to the edge. Each event has a location and a time, and space-time is the full arrangement in which all such events are related. When space-time is flat and no forces interfere, an object moves along the most direct possible route through this combined structure. That route is not merely a line through space, it is a path through space and time together. Physicists call such a path a world line, though the idea is less dramatic than the name suggests. Your world line is simply the sequence of events that make up your motion through the universe. Sitting still in a chair still counts as motion through space-time because time continues to pass, even if the chair is doing very little to improve the situation. Curvature changes the available paths. A planet orbiting a star is not being pulled along by a hidden cable. It is following a natural route through the curved space-time created by the star. The orbit looks like a curved path through space, but in space-time it is the result of moving as freely as possible through a geometry that is not flat. This is one of the most important changes introduced by general relativity. Gravity stops being treated as an ordinary force acting across empty space. Instead, matter and energy influence the geometry of space-time, and that geometry guides the motion of matter and light. The familiar statement is that matter tells space-time how to curve, while curved space-time tells matter how to move. It is a convenient summary, though the complete physics includes pressure, energy flow, and other properties as well as mass. Consider the Earth moving around the Sun. In an older picture, the Sun pulls the Earth inward while the Earth moves sideways, producing an orbit. This picture works very well for many calculations. General relativity gives a deeper description. The Sun alters the geometry around it. Earth follows a path through that geometry. If the Sun could suddenly vanish, which it cannot do without causing several serious scheduling problems, Earth would not respond instantly. Changes in gravity travel at the speed of light. The geometry would adjust outward, and only after that change reached Earth would the planet leave its former orbit. The same geometry affects light, even though light has no rest mass. This was one of the striking predictions of general relativity. Light passing near a massive object follows the straightest path available, but the space-time through which it moves is curved. To a distant observer, the light appears to bend. Astronomers observe this effect when a massive galaxy or cluster lies between Earth and a more distant object. The foreground mass can bend the light from the background source, producing stretched arcs, repeated images, or bright rings. This is called gravitational lensing. It allows scientists to detect matter that does not shine, estimate the mass of galaxy clusters, and study objects too distant to see clearly without nature providing an enormous and rather inconveniently placed telescope. None of this requires space-time to behave like a physical substance. The word fabric is common because it gives us something visual to work with. But space-time has no known threads. It does not flap, crease, or need ironing. Curvature is a statement about measurements and relationships. It tells us how paths separate or converge, how clocks compare, and how the direction of motion changes from one place to another. Clocks provide one of the clearest signs. A clock closer to a massive object runs more slowly relative to a clock farther away. This does not mean the lower clock is damaged or struggling under pressure. Every local process follows the same slowed rate when compared with the distant clock. Chemical reactions, electronic signals, biological aging, and the motion of the clock mechanism all agree. A person standing beside the lower clock notices nothing unusual. Their heartbeat feels normal. Their thoughts proceed normally. Only when signals are compared between different gravitational conditions does the difference appear. This effect exists on Earth. A clock at sea level runs slightly more slowly than one at higher altitude because it is deeper in Earth's gravitational field. The difference is tiny, but modern atomic clocks are sensitive enough to measure changes produced by surprisingly small differences in height. Raise a sufficiently precise clock and it gains time relative to one left below. That may sound like a laboratory curiosity, but it matters in everyday technology. Satellites used for navigation carry very accurate clocks. Their motion and their position higher in Earth's gravitational field both change their rate relative to clocks on the ground. The system must correct for these effects. Without the corrections, errors would grow quickly, and a device trying to guide you to a nearby address might become increasingly confident about a location you never intended to visit. Curvature also reveals itself through tidal effects. Suppose two small objects are released side by side above Earth. Both fall, and because their paths point roughly toward Earth's center, they move slightly closer together as they descend. Locally, each object is freely falling. Neither feels a force pushing it sideways, yet the distance between their paths changes. This relative change is a sign of curvature. Now imagine one long object falling toward a compact mass. The end closer to the mass experiences a different gravitational condition from the end farther away. The object can be stretched along its length and compressed across its width. Near a black hole, these tidal effects can become enormous. They are not caused by gravity being merely strong at one point. They arise because gravity changes significantly from one part of the object to another. This difference helps separate strong gravity from strong curvature. It is possible to be in a region where the gravitational effect is large but nearly uniform across your body, so you feel little tidal stress while freely falling. It is also possible for curvature to be severe enough that nearby paths rapidly separate or converge. What matters for damage is often not the overall pull, but how quickly the pull changes across a distance. The event horizon of a large black hole illustrates this well. From far away, the horizon marks the boundary beyond which signals cannot return. For a traveler falling into a supermassive black hole, crossing that boundary might involve no sudden local event. There is no solid surface, flash, or sign saying that exits are no longer available. The traveler continues falling. The change is global rather than locally dramatic. After crossing, every future directed path leads deeper inward. A distant observer describes the process differently. Light signals from the falling traveler become increasingly delayed and redder. The traveler appears to slow near the horizon, fading from view. The traveler, however, crosses the horizon in a finite amount of personal time. Both descriptions are consistent because they refer to different ways of assigning times and comparing events in curved space-time. This is why ordinary language can struggle. We are used to one shared time and one obvious description of motion. Curved space-time does not always provide either. Time can pass at different rates in different places. Observers can use different coordinates while agreeing on the physical events. A coordinate can behave badly even when the underlying geometry is perfectly regular. The horizon was once confused with a singular problem partly for this reason. In certain coordinates, the mathematical description appears to misbehave at the horizon. Better coordinates remove the problem, showing that the horizon itself is not a place where space-time necessarily breaks. The central singularity is different. There, the signs of trouble cannot be removed merely by changing the labels used to describe events. To see why bending does not require an edge, return to the surface of Earth. The surface is curved, but a traveler can keep moving without reaching a crack where geometry stops. Curvature can be smooth and continuous. Space-time around the sun is curved in the same general sense. It does not have a visible seam where the curved region begins. The effect weakens gradually with distance. Even empty regions can contain curvature. A gravitational wave can move through a region with no nearby matter, altering distances as it passes. Two freely floating objects may move slightly closer and farther apart in a repeating pattern. The wave is not matter traveling through space in the usual way. It is a propagating change in the geometry itself. Calling this a ripple is helpful, but once again the comparison has limits. Water waves move through water. Sound waves move through air or another material. Gravitational waves do not need a separate substance carrying them. They are changes in space-time geometry that move outward from accelerating masses. When two black holes orbit each other, their changing gravitational field produces these waves. The waves carry energy away, causing the orbit to shrink. The black holes move faster, the signal grows stronger, and eventually the objects merge. Afterward, the new black hole settles into a stable shape by sending out a final pattern of waves. Detectors measure these disturbances by comparing lengths in different directions. As a wave passes, one separation can increase while another decreases. Then the pattern reverses. The changes are extraordinarily small by the time they reach Earth. Detecting them requires isolated instruments, careful control of noise, and the willingness to take tiny movements very seriously. A passing gravitational wave does not usually damage anything. Its effect is far too weak at Earth. Closer to the source, the distortion can be much stronger, but the geometry still behaves according to the theory. It changes rapidly without tearing. This suggests that bending, stretching, and vibrating are normal abilities of space-time rather than signs of failure. How far can that bending go? General relativity does not impose a simple maximum curvature in the way a metal beam has a rated load. The equations allow curvature to grow as matter and energy become more concentrated. Under certain conditions, collapse continues toward a singularity. That is where predictions become incomplete and where many physicists expect quantum effects to become essential. Before reaching that limit, however, curved space-time can produce many extreme results while remaining describable. It can slow clocks. It can trap light. It can change the apparent shape of distant galaxies. It can make orbits rotate in ways not predicted by older gravity. It can carry waves across the universe. It can allow two observers to disagree about distances and durations while maintaining a consistent account of cause and effect. One famous test involved the orbit of Mercury. The point of Mercury's closest approach to the Sun slowly shifts over time. Most of that motion can be explained through the influence of other planets, but a small remainder resisted a complete explanation using Newtonian gravity. General relativity accounted for the extra shift through the curvature of space-time near the Sun. It was not a huge effect, but it was exactly the sort of detail that reveals when a deeper theory is needed. Another early test came from observing starlight passing near the Sun. During a total solar eclipse, stars close to the Sun's position could be seen and compared with their usual locations. Their light appeared displaced because it had traveled through curved space-time near the Sun. Later measurements became far more precise, but the principle remained the same. These examples show that curvature is not only an idea used for black holes in the beginning of the universe. It is present around Earth, the Sun, your body, and every object with energy. The curvature created by a person is far too small to notice without impossibly sensitive equipment, but it is not exactly zero. Moving a cup from one side of a table to the other slightly changes the distribution of energy and therefore slightly changes the geometry. The universe copes with this without complaint. Pressure also contributes to curvature. In daily life, we think of gravity as coming from mass. Relativity uses a broader source. Energy, momentum, pressure, and stress all play roles. Inside a dense star, pressure can be enormous, and its contribution to gravity can no longer be ignored. This creates an unusual situation. Pressure helps support a star against collapse, but the energy associated with that pressure also adds to the gravitational effect. For ordinary stars, stable balances are possible. Heat and internal pressure resist gravity. In white dwarfs and neutron stars, quantum properties of matter provide additional forms of support. Yet, there are limits. If a collapsed core is too massive, known forms of pressure cannot hold it up. The geometry continues to change and a black hole forms. This process is not a heavy object pressing down on a cosmic sheet. The collapse happens in all directions. Space and time around the matter change together. The future paths available to particles tilt inward until escape is no longer possible. The phrase tilting inward is another visual aid, but it captures an important point. Inside the horizon, moving towards smaller distance from the center becomes as unavoidable as moving toward tomorrow is for us outside. That is a stronger statement than saying the gravitational pull is difficult to resist. A powerful rocket cannot simply point outward and escape from inside the horizon. The issue is not a lack of engine power. There is no future-directed route leading back outside. Trying to escape would be like trying to travel to yesterday by driving north. More speed does not solve a problem created by the structure of available directions. This helps us understand the difference between bending spacetime and breaking it. Bending changes the relationships among paths, clocks, and events. It can produce conditions that look extraordinary from an ordinary human viewpoint, but the geometry may remain smooth. Breaking would require something more. It might mean that the geometry ends, becomes undefined, changes its basic character, or can no longer support a predictable connection between past and future. A black hole horizon does not automatically meet that definition. A gravitational wave does not meet it. Time dilation does not meet it. Light bending around a galaxy does not meet it. These are all examples of space-time working as general relativity says it should. The singularity predicted inside a black hole is the more serious candidate. So is the earliest stage of the universe when densities and temperatures were extreme enough that classical geometry may no longer apply. In those settings, the smooth space-time picture could be incomplete. The difficulty is that we cannot answer what replaces it until we understand gravity at the quantum level. There may be no literal object called space-time underneath the mathematics. Geometry could be fundamental, or it could emerge from something deeper. If it emerges, curvature may be the large-scale behavior of microscopic relationships we have not yet fully identified. Bending would then be a change in how those underlying parts are arranged, while breaking might be a transition into a state where the familiar idea of distance and duration no longer works. For now, the safest understanding is direct and practical. Space-time bends when the measured relationships among motion, distance, and time differ from those of flat space-time because matter and energy are present. Objects follow altered natural paths. Light changes direction. Clocks disagree after traveling through different gravitational conditions. Nearby falling paths converge or separate. These effects are not decorative metaphors. They are measured features of the universe. The rubber sheet picture can help us begin, but it leaves out time, relies on Earth's gravity to demonstrate gravity, and suggests an outside space that the real theory does not require. A better picture is a network of clocks and freely moving objects spread through a region. Watch how the clocks compare. Watch how the objects move relative to one another. Send light between them. If their relationships cannot be described by flat geometry, curvature is present. Once curvature is understood in that way, the next question becomes more focused. What creates enough curvature to move from the gentle fields around planets into the extreme conditions around collapsed stars? The answer begins with gravity as the universe's quiet sculptor, shaping paths and clocks everywhere, usually so gently that we mistake its work for the ordinary background of life. Gravity is always working, even when nothing seems to be happening. It holds the ocean against the Earth, keeps the moon in orbit, guides the planets around the sun, and gathers enormous clouds of gas into stars. It shapes galaxies over billions of years and influences the path of every beam of light that crosses the universe. Most of the time, it does all of this quietly. There is no sound of space bending, no visible hand pulling objects together, and no warning bell when one mass begins to influence another. Gravity simply changes the routes that matter and light are able to follow. This quietness can make gravity seem less dramatic than it really is. Electromagnetism gives us lightning, sparks, glowing screens, and the small but memorable shock of touching a metal handle after walking across a carpet. The strong nuclear force helps power the reactions inside stars. Gravity often appears to do little more than keep our feet on the ground and cause dropped objects to choose the least convenient possible landing place. Yet on the scale of planets, stars, galaxies, and the universe itself, gravity becomes the main architect. Its influence begins with the fact that every form of mass and energy contributes to space-time curvature. A grain of sand curves space-time. A person sitting in a chair curves space-time. The chair contributes too, although not enough to demand recognition. These effects are extremely small, but they are real. Add enough matter together, and the curvature becomes strong enough to guide moons, bend light, and slow clocks by measurable amounts. The shape created by gravity is not fixed in the same way as a sculpture carved from stone. Matter moves, energy flows, stars burn, planets orbit, and galaxies collide. The geometry changes in response. Gravity is therefore less like a finished statue and more like a sculptor that never stops working. It pushes nothing with hands, but it continuously reshapes the possible paths through space and time. Near Earth, the effect is gentle enough that Newton's description of gravity works very well. Objects fall with predictable acceleration. The moon follows its orbit. Satellites can be guided around the planet. Engineers can build bridges, launch rockets, and calculate trajectories without treating every problem as a full investigation of curved space-time. General relativity remains underneath the process, but its corrections are often so small that they can be safely ignored. This is useful because the complete geometry of space-time can be difficult to describe. Nature does not insist that we use the most advanced theory for every ordinary task. You would not need a detailed model of molecular chemistry to decide whether a cup is full. In the same way, Newtonian gravity is usually enough to understand a falling apple, although the apple itself may not appreciate being used in so many physics examples. The deeper picture becomes necessary when gravity is strong, when precision is important, or when objects move at very high speeds. The orbit of Mercury required it. The behavior of clocks and navigation satellites requires it. Black holes demand it completely. In these situations, gravity cannot be treated as a simple pulling force without losing important parts of what is happening. To see how gravity sculpts on a large scale, imagine a wide region of space filled with thin gas. The gas is not perfectly smooth. Some areas contain slightly more matter than others. Those denser regions create slightly stronger gravitational effects. Nearby gas drifts toward them, making them denser still. As more material gathers, the attraction increases. A tiny unevenness can therefore grow into a large structure. This process helped shape the early universe. Matter collected around small differences in density. Over immense spans of time, those differences developed into the structures that would become galaxies and galaxy clusters. Gravity took a universe that was once much smoother and drew matter into filaments, sheets, knots, and wide empty regions. The result resembles a web on the largest observable scales. Galaxies are not scattered entirely at random. They gather along vast structures, with clusters sitting where several filaments meet. Between them are enormous voids containing much less matter. Gravity created this pattern slowly, drawing material toward regions that already had a slight advantage. Dark matter played a major role in that growth. It does not emit, reflect, or absorb light in the usual way, which makes it difficult to observe directly. Its gravitational influence, however, can be measured. Galaxies rotate as though they contain more mass than their visible stars and gas can provide. Light from distant objects bends around galaxy clusters more strongly than the visible material alone would explain. The large-scale structure of the universe also fits models in which dark matter provided much of the gravitational framework around which ordinary matter gathered. In that sense, many galaxies grew inside invisible gravitational structures. Gas fell inward, cooled, and formed stars. Those stars gathered into rotating systems. More gas arrived. Smaller galaxies merged into larger ones. Gravity did not plan the result, but over time it produced spirals, elliptical galaxies, clusters, and long streams of stars pulled from one system by another. Our own galaxy carries evidence of this ongoing work. The Milky Way contains a broad disk of stars, gas, and dust, surrounded by a much larger region influenced by dark matter. Smaller galaxies orbit nearby, some are being slowly disrupted. Their stars are stretched into long streams as the Milky Way's gravity pulls different parts of them with different strength. Once again, tidal effects are doing the sculpting. The side of a small galaxy closer to the Milky Way feels a stronger gravitational influence than the far side. Over many orbits, this difference can draw stars away. A galaxy that once held itself together becomes a faint trail spread across space. Nothing struck it. There was no sudden collision. Gravity changed its shape by applying slightly different conditions across its width for a very long time. Tides on Earth are a familiar version of the same idea. The moon pulls more strongly on the side of Earth nearest to it and less strongly on the far side. This difference contributes to the rise and fall of the oceans. The sun also affects the tides. The result depends on the positions of Earth, moon, and sun, as well as the shape of coastlines and the depth of the sea. It is tempting to say that the moon simply pulls the water upward, but the full motion involves the entire Earth and its oceans responding to a changing gravitational field. The same principle that stretches a moon, disturbs an ocean, or tears stars from a galaxy can become far more severe near compact objects. Before reaching those extremes, gravity first shapes stars themselves. A star begins in a cold cloud containing gas and dust. The cloud may be disturbed by a nearby stellar explosion, a collision with another cloud, or the slow growth of an already dense region. Once enough material gathers, gravity draws the cloud inward. As it collapses, the gas becomes denser. Particles collide more often, and the temperature rises. The cloud may fragment into several smaller collapsing regions, creating multiple stars rather than one. Disks of material can form around the young stars. Within those disks, grains collide and stick together, eventually building rocks, asteroids, planets, and moons. Everything in a solar system therefore carries the history of gravitational gathering. The material in Earth was once spread through a cloud. Gravity helped bring it together, though the details also involved collisions, chemistry, heat, and the behavior of gas and dust. The planet beneath you is part of a structure assembled through countless interactions over a period much longer than any human life can easily picture. At the center of a forming star, pressure and temperature continue to rise. Eventually, conditions become intense enough for nuclear fusion to begin. Light atomic nuclei combine into heavier ones, releasing energy. That energy moves outward and helps resist further collapse. A stable star lives in a long balance between gravity pulling inward and pressure pushing outward. Neither side wins completely. If gravity won, the star would collapse. If outward pressure won, the star would disperse. Instead, the two tendencies maintain a structure that can remain steady for millions, billions, or even much longer periods, depending on the star's mass. The sun has maintained this balance for billions of years. Deep in its core, fusion releases energy. That energy slowly makes its way outward before escaping as sunlight. Gravity holds the star together while pressure keeps the core from collapsing further. The sunlight warming Earth today began as energy produced in a region where matter is compressed by the weight of everything above it. Stars of different masses live differently because gravity determines the conditions in their cores. A low-mass star compresses its center less severely and burns fuel slowly. It can remain active for an extremely long time. A high-mass star has much stronger gravity. Its core becomes hotter and denser, allowing fusion to proceed rapidly. It shines brightly but uses its fuel quickly. This creates one of the universe's common reversals. Having more fuel does not always mean living longer. A massive star contains far more material than the sun, yet it may survive for only a small fraction of the sun's lifetime. Its stronger gravity drives a much faster rate of fusion. It lives with the energy habits of someone who has discovered an unlimited buffet and misunderstood the word unlimited. As stars age, gravity continues shaping their internal structure. When hydrogen becomes scarce in the core, the balance changes. The core contracts and heats while the outer layers expand. A star like the sun will become a red giant. Its outer atmosphere will spread far beyond its present size while the center prepares for a new stage of fusion. Eventually, a sun-like star releases its outer layers into space. The remaining core becomes a white dwarf. This object contains a large amount of mass compressed into a volume roughly comparable to Earth. It no longer produces energy through normal stellar fusion. Instead, it remains supported against further collapse by a quantum effect associated with electrons. This support does not behave like ordinary gas pressure. It arises because identical particles cannot all occupy the same quantum state. Compressing the matter forces electrons into increasingly energetic arrangements. Their resistance can support the white dwarf, but only up to a certain mass. Gravity therefore meets its first major obstacle in the quantum behavior of matter. If the white dwarf remains below its limiting mass, it can exist for an extremely long time, gradually cooling. Add too much material, perhaps by drawing gas from a nearby companion star, and the balance can fail. The result may be a powerful explosion or further collapse, depending on the circumstances. More massive stars develop even hotter cores and can fuse heavier elements. They build layered structures with different nuclear processes occurring at different depths. The sequence cannot continue forever. Fusion involving iron does not provide the same outward energy benefit as earlier stages. Once an iron-rich core becomes too massive, the star loses a crucial source of support. Collapse then proceeds very quickly. The core contracts under gravity, particles are forced into extreme conditions, and the outer parts of the star fall inward. A violent rebound and the release of enormous amounts of energy can produce a supernova. For a brief period, a single exploding star may shine with the brightness of an entire galaxy. The explosion spreads newly formed elements into space. Carbon, oxygen, silicon, iron, and many heavier elements become part of future clouds, stars, planets, and living things. Gravity gathers matter, stars transform it, explosions distribute it, and gravity gathers it again. The calcium in bones, the iron in blood, and many of the elements around us passed through stellar processes before the solar system existed. What remains after a massive star's collapse depends largely on the mass of the core. In some cases, the remnant becomes a neutron star. Here, gravity has compressed matter far beyond the density of a white dwarf. Electrons and protons are forced into processes that produce neutrons, and the remaining object can contain more mass than the Sun within a sphere roughly the size of a city. A small amount of neutron star material would have an astonishing mass under ordinary Earth conditions. The exact comparison depends on the object and the amount chosen, but the main point is clear. Matter has been packed into a state that cannot be reproduced in a kitchen, no matter how ambitious the appliance collection. The surface gravity of a neutron star is immense. A falling object would reach tremendous speed before impact. Light leaving the surface loses energy as it climbs outward, shifting toward longer wavelengths. Clocks near the surface run more slowly relative to distant clocks. The star also bends the paths of light so strongly that an observer may see portions of the surface that would normally be hidden around the curve. Some neutron stars rotate rapidly and produce beams of radiation from regions near their magnetic poles. When those beams sweep across Earth, astronomers detect regular pulses. These objects are called pulsars. Their signals can be remarkably stable, turning the remnants of dead stars into some of the most precise natural clocks known. Others possess magnetic fields of extraordinary strength. These magnetars can release sudden bursts of high-energy radiation. Their crusts may crack as the intense magnetic field changes, producing events sometimes described as star quakes. The space-time around them remains curved by the star's mass, while the material inside is stressed by forces difficult to reproduce anywhere else. A neutron star shows how far gravity can compress matter without necessarily forming a black hole. It is a place where gravity, quantum physics, nuclear forces, pressure, and rotation all compete. The exact behavior of matter deep inside remains uncertain. It may contain forms of particles or phases of matter not found under ordinary conditions. There is still a limit. If the core is too massive, even neutron-based support cannot prevent further collapse. The escape speed rises, the geometry becomes more extreme, and an event horizon forms. Gravity has then created a black hole. The phrase escape speed is useful from a distant perspective, but a black hole is not simply an object with an unusually powerful pull. It changes the causal structure of space-time. Outside the horizon, outward paths still exist. At the horizon, the boundary marks where escape to the distant universe becomes impossible. Inside, all future-directed paths move towards smaller distances from the center. A black hole can be described using a surprisingly small number of visible properties. Its mass matters, its rotation matters, its electrical charge could matter, though astrophysical black holes are expected to carry little lasting charge because surrounding matter would tend to neutralize it. Much of the complicated information about the star that collapsed becomes hidden from an outside observer. Gravity simplifies the exterior while making the interior deeply uncertain. From the outside, the black hole can be modeled with great precision. Matter may orbit it in a disk. Friction and magnetic effects heat that material until it shines brightly. Jets can be launched from regions near some black holes, powered by processes involving rotation, magnetic fields, and the surrounding plasma. The black hole itself emits no ordinary light from inside the horizon. The bright display comes from matter that has not yet crossed. This distinction is often lost in dramatic images. A black hole surrounded by a luminous disk is not glowing. It is the dark region around which nearby material is having a very difficult day. Supermassive black holes sit at the centers of most large galaxies. They contain millions or billions of times the mass of the Sun. Their origin and growth are still active areas of study. Some may have begun from the collapse of early massive stars. Others may have formed from the direct collapse of large gas clouds. Mergers and long periods of feeding allowed them to become enormous. Their gravity influences stars nearby, but it does not normally hold an entire galaxy together by itself. The mass of a supermassive black hole is usually small compared with the total mass of its host galaxy and dark matter halo. It dominates the central region while the larger galactic structure depends on much more widely distributed matter. When actively feeding, these black holes can power quasars, some of the brightest objects in the universe. Gas falling inward releases gravitational energy before crossing the horizon. The surrounding disk can outshine the stars of the entire host galaxy. Gravity, usually so quiet, becomes responsible for a beacon visible across enormous distances. Even then, gravity is not acting alone. Magnetic fields twist through the disk, radiation pushes on matter, collisions heat the gas, particles interact in complicated ways. Gravity creates the environment and controls the overall motion, while other forces shape the details. This partnership appears throughout the universe. Gravity gathers, compresses, and organizes. Other forces determine how matter resists, heats, shines, reacts, and changes state. A planet exists because gravity pulled material together, but its solid surface depends on electromagnetic bonds between atoms. A star exists because gravity compresses its core, but its energy comes from nuclear reactions. A neutron star survives because quantum and nuclear effects resist further collapse. Gravity becomes dominant at large scales, partly because it always attracts under ordinary conditions. Positive and negative electrical charges can cancel one another. Matter is usually close to electrically neutral. Overall, gravity has no familiar negative mass that cancels ordinary positive mass. Every contribution adds to the total influence. It is also long-ranged. Its strength decreases with distance, but it never reaches a simple edge where it becomes exactly absent. The Sun influences distant objects. The Milky Way affects nearby galaxies. Galaxy clusters pull on one another across vast regions. Over enough time, even a weak effect can reshape motion. This long reach allows gravity to sculpt slowly. A collision is not always needed. Orbits can change over millions of years. Galaxies can draw together over billions. Stars in dense clusters can exchange energy through repeated encounters. Planets can migrate through young disks. Moons can move gradually outward or inward as tides transfer energy and rotation. Earth and the Moon provide a gentle example. The Moon's gravity raises tides on Earth. Because Earth rotates faster than the Moon orbits, the tidal bulges are carried slightly ahead of the direct line between them. Their gravitational influence transfers rotational energy from Earth to the Moon. Earth's rotation slowly decreases while the Moon gradually moves farther away. The changes are small over a human lifetime. But gravity has no objection to patience. Given enough time, tiny transfers can become important. Days on the early Earth were shorter, the Moon was closer. The system has been evolving continuously. The same tidal processes can heat moons around giant planets. A moon following a slightly stretched orbit experiences changing gravitational stress. Its interior flexes, producing heat. This can drive volcanic activity or help maintain oceans beneath an icy surface. Gravity therefore shapes not only paths but also internal environments that may affect whether a world can support interesting chemistry. Jupiter's moon Io is heated intensely by tidal flexing and is covered with active volcanoes. Europa may contain a global ocean beneath its ice, with tidal energy helping prevent complete freezing. Far from the warmth of the sun, gravity can provide another energy source. Near black holes, tidal sculpting becomes destructive. A star passing too close can be pulled apart. The near side accelerates differently from the far side until the star's own gravity can no longer hold it together. Some material escapes while some falls toward the black hole and forms a hot, bright stream. These tidal disruption events allow astronomers to study otherwise quiet black holes. The black hole becomes noticeable because a star wandered into the wrong region and was converted into a temporary signal. Gravity does not need to strike the star. It separates the paths of its different parts until the star can no longer remain one object. Still, even the destruction of a star does not mean space-time has failed. The geometry may be extreme, but it continues guiding matter according to predictable rules. The sculpture can be violent without the sculpting medium breaking down. The true limits appear when gravity compresses matter beyond every known form of support or drives curvature toward conditions where general relativity predicts a singularity. That is where the quiet sculptor begins to work with pressures and densities that challenge the tools used to describe it. A normal star can resist. A white dwarf can resist more. A neutron star can endure conditions that would crush ordinary matter beyond recognition. Each stage reveals another level of support, and each support has a boundary. Add enough mass, remove enough energy, or disturb the balance severely enough, and gravity resumes the collapse. The next step is not simply a stronger version of an ordinary star. It is a change in the structure of space-time around the object. Horizons can form. Light can become trapped. The future paths of matter can be redirected inward in a way no pressure can reverse once the critical condition is crossed. To understand how close this comes to breaking space-time, we need to follow the lives of the largest stars into their final moments. Their gravity no longer shapes gently over billions of years. It acts in seconds, compressing stellar cores, driving explosions, and forcing matter towards states where the familiar structure of space and time begins to face its most severe test. The largest stars do not approach their final moments quietly. For most of their lives, they maintain the same basic agreement that keeps every stable star intact. Gravity pulls the material inward while pressure from the hot interior pushes outward. The balance is never permanent, but it can last for millions of years. Then the fuel begins to run out. The internal structure changes, and gravity starts asking questions that matter can no longer answer easily. A massive star lives under far greater pressure than a star like the Sun. Its own weight compresses the core so strongly that nuclear reactions proceed at an extraordinary rate. Hydrogen is converted into helium. Later, helium is used to build heavier elements. As one source of fuel becomes exhausted, the core contracts and heats, making another stage of fusion possible. This process creates a layered interior. Near the outside, lighter elements remain. Deeper down, heavier elements are being produced. The star begins to resemble an onion, though an onion with a surface hot enough to make chopping it a fairly brief experience. Each layer contains different reactions, and each reaction helps provide the energy needed to resist gravity. The sequence continues through several elements, but it eventually reaches iron. Iron creates a serious problem. Earlier fusion reactions release energy when lighter nuclei combine. That energy helps heat the star and maintain pressure. Combining iron into heavier elements does not release energy in the same useful way. It requires energy instead. The core can therefore reach a point where it is still gaining iron but no longer gaining enough support. Gravity continues pressing inward. The pressure that held the star stable begins to weaken. The balance that lasted through the star's life can fail with remarkable speed. The iron core does not need to be as large as the whole star. It may contain an amount of mass similar to the Sun packed into a region much smaller than Earth. The material is extremely hot and dense, but temperature alone cannot stop what follows. Once the core passes its limit, it begins to collapse. At first, the collapse makes the core hotter. Under many ordinary conditions, heating a gas increases its pressure and helps it resist compression. Inside the collapsing core, several processes work against that rescue. High-energy light begins breaking iron nuclei into smaller pieces. This consumes energy. Electrons are forced into protons, producing neutrons and releasing particles called neutrinos. This reduces the pressure provided by the electrons. The core loses support at the very moment gravity is demanding more of it. Matter falls inward at a significant fraction of the speed of light. A structure larger than a planet can change completely in less time than it takes to decide whether you heard something outside. The collapse continues until the central matter reaches enormous density. Atomic structures cannot survive in their familiar form. The core becomes mostly neutron-rich matter, and new forms of pressure begin resisting further compression. The inner region suddenly stiffens. Material still falling inward strikes this compressed core and slows sharply. This produces a shock wave that begins moving outward. The simple picture suggests that the shock should tear through the star and cause an explosion immediately. In detailed models, the shock can lose energy and stall. The star is not easily persuaded to explode merely because the first attempt looked promising. Neutrinos become important at this stage. Huge numbers of them are produced in the collapse. They usually pass through matter with very little interaction. But the collapsing core is so dense that even neutrinos struggle to escape immediately. As they move outward, some of their energy can help revive the stalled shock. The full process is complicated and remains an active subject of research. Rotation, magnetic fields, turbulence, the star's original structure, and the behavior of matter at extreme density all affect the outcome. The general result when the explosion succeeds is a core collapse supernova. The outer layers of the star are thrown into space at tremendous speed. For a short period, the explosion can shine brighter than billions of ordinary stars. The event produces and distributes many heavy elements. Material that spent millions of years buried inside the star is scattered into the surrounding galaxy, where it may later become part of new stars, planets, rocks, oceans, and living organisms. A supernova is therefore both an ending and a source of raw material. The star loses most of its outer structure, but its elements continue participating in the universe. Gravity may gather them into another cloud, a new star may form, planets may grow around it. Much later, someone on one of those planets might look upward and ask why the universe appears to have made everything so complicated. The central remnant is where our question becomes more serious. If the remaining core is light enough, it can settle as a neutron star. The collapse has compressed more mass than the Sun into a sphere only a few tens of kilometers across. Matter there is unlike anything found naturally on Earth. A neutron star is not simply a giant ball made from loose neutrons. Its structure may include several layers. The outer crust contains nuclei and electrons under immense pressure. Deeper regions become increasingly neutron-rich. Farther in, the matter may contain free neutrons, superconducting protons, unusual particles, or other states that are still uncertain. Scientists can study neutron stars through their masses, radii, rotation, radiation, cooling, and behavior during collisions. These observations help narrow the possible descriptions of matter at extreme density. Even so, the exact condition of the deepest core remains unknown. What is clear is that neutron stars have limits. The quantum and nuclear effects supporting them can resist gravity only up to a certain amount of mass. The exact maximum depends on how dense matter behaves, which is one reason measuring heavy neutron stars is so important. Each confirmed object tells physicists that matter must be stiff enough to support at least that much weight. A neutron star near its maximum mass is already pushing space-time into severe curvature. A clock near the surface runs significantly more slowly than a distant clock. Light leaving the star loses energy. The path of light bends enough that an observer can see more than half of the surface at once. The star may rotate hundreds of times each second. This rotation slightly changes its shape and can help support it against collapse. A rapidly spinning object gains a temporary advantage because rotation resists some of gravity's inward effect. It is not an unlimited advantage. The star cannot rotate arbitrarily fast without becoming unstable or throwing matter away. Magnetic fields can also affect the star, especially in magnetars, but they do not provide a simple escape from the mass limit. If the core becomes too heavy, gravity eventually wins. There are several ways this can happen. The neutron star may be born with too much mass after a supernova. It may pull material from a companion star. It may merge with another neutron star. It may also begin its life supported partly by rapid rotation, then collapse later as it loses rotational energy. That delayed collapse would be a strange event. For some time, the star might appear stable. It would spin, emit radiation, and behave like an extremely compact but recognizable object. As the rotation slowed, the extra support would weaken. At a critical point, the star could collapse into a black hole. From the outside, this transition might happen quickly. The surface would move inward. The curvature would grow. A horizon would form once enough mass had been compressed within a sufficiently small region. After that boundary appeared, light from inside could no longer reach distant observers. Nothing needs to strike the star from outside. No cosmic hammer is required. The weight of the star itself provides the condition. Gravity takes the energy and matter already present and concentrates them until the structure of space-time changes in a fundamental way. This is the first place where the idea of pushing space-time too far begins to sound reasonable. The star does not tear space-time like cloth. It curves space-time until a region becomes causally separated from the outside universe. Events inside can still influence other events inside, but they cannot send signals beyond the horizon. The word horizon is important because it describes a boundary in information, not a physical shell. An event horizon is not made from matter. It does not have a solid surface that an object crashes into. It marks the point beyond which no future directed path leads back outside. For a small black hole, the tidal effects near the horizon can be extremely strong. An object falling toward it would be stretched because the side closer to the black hole follows a noticeably different path from the side farther away. The difference can become strong enough to pull matter apart before it crosses. A very large black hole can be different. Its horizon lies farther from the central region, where tidal changes across a human body may be relatively mild. A falling observer could cross the horizon without feeling a sudden jolt at that exact moment. There would still be no route back, but the local environment might not announce the crossing. This can feel unsatisfying because boundaries are expected to look like boundaries. A coastline separates land from sea. A door separates one room from another. The event horizon separates possible escape from unavoidable inward motion, yet it may have no local marker. Its meaning depends on the full future of space-time. To know whether an event lies inside a black hole, we ask whether light from that event can ever reach far away. This makes the horizon a global feature. It is defined not only by what is happening nearby at one moment, but by how the space-time develops. During the collapse of a star, the horizon can form before the material reaches the central region. Light emitted after that formation remains trapped. The star continues collapsing inside, hidden from distant view. Outside, the gravitational field settles toward that of a black hole. A distant observer watching the stellar surface sees its signals become weaker and more delayed as the surface approaches the horizon. The light becomes increasingly redshifted. In the distant observer's chosen time coordinate, the surface appears to slow and fade. The falling material experiences its own time normally. It crosses the horizon and continues inward. There is no contradiction because the two descriptions compare events in different ways. Relativity allows both accounts without requiring either observer to be mistaken. Once inside, collapse continues. Classical general relativity predicts that the matter reaches a singularity. This is not merely a point where density becomes inconveniently high. It represents a failure in the usual description of space-time. Paths can end after a finite amount of personal time. Curvature becomes unbounded in the mathematical model. The theory no longer provides a complete continuation. That sounds very much like space-time breaking, but caution is needed. The singularity may be a genuine feature of nature, or it may signal that general relativity has been used beyond its valid range. Most physicists expect quantum effects to matter before an actual infinite density is reached. The problem is that the conditions are hidden behind the horizon and far beyond what current experiments can reproduce. We cannot place instruments at the center of a black hole. We cannot receive a signal describing the final state. We must build theories that agree with known physics and look for effects that might appear outside. Several ideas attempt to replace the classical singularity. Some suggest that gravity becomes repulsive at extremely small scales, stopping the collapse. Others propose that space-time is made from discrete structures and cannot be compressed without limit. Certain models replace the central point with a small but finite region containing quantum gravitational effects. There are also proposals involving a bounce where collapse leads into another expanding region. Some suggest connections with white holes, hypothetical objects from which matter can emerge but cannot enter. These possibilities are interesting, but none has been confirmed as the correct description of real black hole interiors. The uncertainty should not be mistaken for complete ignorance. General relativity gives reliable predictions outside the deepest region. Astronomers can measure the motion of stars around black holes, study hot gas near them, detect gravitational waves from mergers, and image glowing material close to their horizons. The theory has passed every direct test in these environments so far within the precision of the measurements. The problem begins where curvature becomes so extreme that quantum gravity is expected to take over. This creates a strange division. The collapse of a star is understood very well through much of the process. Nuclear physics explains the fuel. Gravity explains the compression. Particle physics helps describe the core collapse. Computer models follow the shock and neutrinos. Relativity describes horizon formation. Then deep inside, the explanation reaches a boundary. The boundary does not arise because physicists have run out of enthusiasm. It arises because the two strongest frameworks available describe nature differently. General relativity treats spacetime as smooth. Quantum physics treats physical systems through quantum states and interactions. Both work extremely well, but combining them under the conditions inside a black hole remains difficult. Stars therefore become natural experiments that push several theories to their limits. A massive star spends its life building heavier elements. Its death compresses matter beyond atomic density. If the remnant is heavy enough, the event creates a region where smooth spacetime may eventually cease to be an adequate description. Not every massive star follows exactly the same route. Some lose much of their material through powerful stellar winds before they die. Some exchange matter with a companion. Some rotate rapidly. Their chemical composition also affects their evolution. A star born with fewer heavy elements may retain more mass and produce a heavier remnant. In certain cases, the star may collapse with only a weak visible explosion. Much of its material can fall directly into the forming black hole. Astronomers sometimes describe this as a failed supernova. The star may brighten briefly or simply disappear from view, leaving a black hole where a luminous object once stood. There may also be stars so massive that they encounter another form of instability. At extremely high temperatures, energetic light can produce pairs of particles and their antimatter partners. This reduces the pressure supporting the core. The core contracts, fusion accelerates, and the resulting explosion can become enormously powerful. For some mass ranges, the star can be completely destroyed, leaving no compact remnant. For even larger cores, the energy released may still fail to reverse collapse, allowing a heavy black hole to form. The exact outcomes depend on the star's mass, composition, rotation, and mass loss. These events show that pushing spacetime too far is not controlled by a single number. Total mass matters, but so does concentration. A diffuse cloud can contain enough material to make many stars without forming one horizon around the entire cloud. The same amount compressed into a smaller region may collapse into a black hole. The shape and motion of the material matter too. Rotation can delay collapse. Pressure can support an object. Radiation can drive material away. Magnetic fields can transfer energy. A companion star can add or remove mass. The path toward a horizon is determined by the full physical condition, not merely by placing a star on a scale. There is still a general rule beneath all this detail. When enough mass and energy become confined within a small enough region, a horizon can form. Once it forms, the central evolution becomes hidden from the outside. This is not a tier that opens into empty nothingness. It is a change in which events can communicate with which other events. The outside universe continues normally. Planets can orbit the black hole. Gas can circle it. Light can pass at a safe distance and escape. A black hole with the same mass as a star produces the same distant gravitational effect as that star, provided rotation and other details are treated appropriately. If the sun were somehow replaced by a black hole of exactly the same mass, Earth would continue along nearly the same orbit. The planet would not be pulled inward simply because the central object had become a black hole. The serious problem would be the disappearance of sunlight, which would quickly make orbital stability feel like a rather small consolation. Black holes become dangerous when objects approach closely, not because they pull the entire universe toward them like drains. Their gravity follows the same principles as any other mass. What makes them extreme is how much mass is concentrated inside the horizon and how severely space-time curves nearby. The collapsing star has therefore not created an object that ignores physics. It has created an object predicted by physics, one that forces us to distinguish between strong curvature and an actual failure of description. The horizon itself can be smooth, the surrounding space-time can be calculated. The apparent breaking point lies deeper, where the classical paths end. Before we can decide whether that hidden region is a true fracture in reality or only a gap in our current knowledge, we need to examine black holes more closely. Their horizons, interiors, mergers, and singularities provide the nearest thing physics has to an edge where space-time may stop behaving as an ordinary continuous geometry. A black hole is often described as the place where gravity becomes so strong that nothing can escape. That description is useful, but it can also make a black hole sound like a very powerful vacuum cleaner roaming through space and collecting anything that happens to come nearby. Real black holes are less eager than that. They do not chase stars, inhale galaxies, or pull distant objects out of stable orbits without reason. From far away, their gravity behaves much like the gravity of any other object with the same mass. The difference appears when something travels close enough to the black hole. There, space-time is curved so strongly that the available paths begin to change in ways that have no ordinary equivalent. Light can orbit temporarily. Clocks can disagree by large amount. Matter can be heated until it shines more brightly than entire groups of stars. Beyond the event horizon, every possible route into the future leads farther inward. This makes the event horizon the natural place to begin. It is the feature that separates a black hole from an ordinary compact object. A neutron star has a surface. Matter falling onto it can strike that surface, heat it, and release radiation. A black hole has no known material surface at the horizon. Falling matter passes through the boundary and continues inward. A distant observer never receives a signal showing the exact moment when something crosses. Light sent from the falling object takes longer to escape as the object approaches the horizon. Each signal arrives weaker, redder, and more delayed than the one before it. Eventually, the object fades from view. From the perspective of the falling object, the experience is different. It reaches and crosses the horizon after a finite amount of its own time. If the black hole is sufficiently large, the crossing may not involve any sudden physical sensation. There is no wall to strike and no visible line painted across space. The traveler may notice the outside universe becoming increasingly distorted, but the horizon itself is not necessarily marked by a local event. The two descriptions are not competing stories. They result from different ways of measuring time and assigning coordinates in curved space-time. The distant observer continues receiving older and increasingly delayed signals. The falling traveler continues along a path that passes through the horizon. This is one reason black holes are difficult to discuss using ordinary language. We expect an event either to happen or not happen at a shared moment. Relativity does not always provide one universal clock that everyone agrees to use. Each observer measures time along their own path, and curved space-time changes how those measurements compare. The horizon also depends on what happens in the future. To decide whether an event is inside a black hole, physicists ask whether any light leaving that event can ever reach the distant universe. If the answer is no, the event lies inside. This means the boundary is defined using the full structure of space-time, not only the local conditions at one instant. That sounds inconvenient, and it is. Nature did not design black holes for easy bookkeeping. In practical situations, physicists can use related boundaries that are easier to identify during a collapse or merger. These boundaries track regions where outward moving light is no longer expanding away as expected. They help researchers simulate changing black holes without needing to know the complete future in advance. For a settled black hole, the event horizon takes a simpler form. Its size depends mainly on the mass and rotation of the black hole. A more massive black hole has a larger horizon. A rotating black hole also drags the surrounding space-time, adding another layer to the geometry. This dragging is called frame dragging. Any rotating mass produces it, including Earth, although Earth's effect is extremely small. Near a rapidly rotating black hole, frame dragging can become so strong that no object can remain completely stationary relative to the distant universe. Space-time itself is carried around the black hole. Outside the horizon of a rotating black hole lies a region called the ergosphere. An object in this region can still escape, but it must move with the rotation to some degree. In principle, energy can be extracted from the black hole's spin by sending matter through carefully chosen paths. Natural processes involving magnetic fields and surrounding plasma may also draw rotational energy from black holes and help power enormous jets. These jets can extend far beyond the galaxy containing the black hole. They are not streams of material coming from inside the horizon. Nothing ordinary escapes from there. The jets form outside where magnetic fields, hot plasma, and rotation interact with the energy available around the black hole. A feeding black hole can therefore become one of the brightest objects in the universe while remaining completely dark itself. Gas spirals inward through a disk. Friction, turbulence, and magnetic effects heat it to extreme temperatures. The gas releases radiation before crossing the horizon. The closer it moves, the more gravitational energy can be converted into heat and light. This process is remarkably efficient. Matter falling toward a black hole can release a larger fraction of its energy than matter undergoing ordinary nuclear fusion inside a star. The black hole does not burn the material. The energy comes from the motion and heating of matter in the curved space-time outside. A black hole that is not feeding can be very difficult to detect. Astronomers may find it by watching a visible companion star orbit an unseen mass. They may observe light from a background star being temporarily magnified as the black hole passes in front. They may detect gravitational waves when it merges with another compact object. The horizon hides the interior, but the exterior still carries information about the black hole's mass and rotation. If it has electrical charge, that can also influence the geometry, though real astronomical black holes are expected to become nearly neutral because opposite charges in surrounding matter would be attracted and collected. This simplicity is sometimes described by saying that black holes have very little hair. The phrase means that most details of the material that formed the black hole are not visible in its settled exterior. A black hole made from collapsing gas and one formed through the merger of smaller black holes can eventually look the same if their mass, rotation, and charge are the same. That creates an immediate puzzle. Ordinary physical processes preserve information in some form. If a detailed object falls into a black hole and the exterior remembers only a few general properties, what happens to all the other information? The question becomes sharper when quantum physics is included. Quantum theory does not allow information to disappear casually. A system can become complicated, mixed, and nearly impossible to reconstruct in practice. But the underlying evolution is expected to preserve the information about its earlier state. Black holes appear to challenge that expectation. They can absorb matter carrying detailed quantum information. According to quantum effects, they can also slowly emit radiation and lose mass. If the black hole eventually evaporates completely and the outgoing radiation contains no record of what fell in, the information seems to have been destroyed. This is known as the black hole information problem. It is not merely a disagreement about where someone left a notebook. It exposes a conflict between general relativity, quantum physics, and the behavior of horizons. The radiation involved is called Hawking radiation. Quantum fields do not become completely inactive near a horizon. The black hole can emit a faint thermal glow, causing it to lose energy and shrink over extremely long periods. For black holes formed from stars, this radiation is far too weak to detect with current instruments. The surrounding universe is warmer than the black hole. Such objects absorb more energy than they lose. Only after the universe becomes much older and colder would evaporation dominate. For isolated stellar black holes, a smaller black hole would be hotter and would evaporate more quickly. As it lost mass, its temperature would rise, increasing the rate of energy loss. The final stage is uncertain because the black hole would eventually become small enough for quantum gravity to matter. The simplest calculation of Hawking radiation makes it appear thermal, meaning the outgoing particles reveal the black hole's temperature but not the detailed state of everything that fell inside. If evaporation ends with no black hole remaining, the original information appears lost. Several possible answers have been proposed. Information might escape gradually through subtle patterns in the radiation. it might remain stored in a small final remnant. It might pass into another region of space-time. The evaporation calculation might need corrections from quantum gravity, or our ordinary assumptions about the inside and outside of the horizon might be incomplete. Many physicists now expect that information is preserved, but the exact mechanism remains a major subject of research. Ideas involving quantum entanglement, holographic descriptions, and the relationship between geometry and information have changed how the problem is approached. The holographic idea suggests that the physics within a region may be fully described by information associated with its boundary. This does not mean the universe is a visual projection in the everyday sense. It means that a theory with gravity inside a volume may be equivalent to another theory without gravity on a lower dimensional boundary. Black holes helped motivate this idea because their entropy, which measures the number of possible hidden microscopic states, depends on the area of the horizon rather than the volume inside. That result is surprising. For ordinary systems, one might expect storage capacity to grow with volume. Black holes point toward a deeper connection between surface area, information, and space-time. This connection has led some researchers to suspect that space-time itself may emerge from quantum information. In certain theoretical models, patterns of entanglement between quantum systems help produce the geometric relationships that appear as distance and connectivity. Change the entanglement, and the geometry changes. If that broad idea is correct, the interior of a black hole may not be an independent region described separately from the horizon. The information on the boundary and the geometry inside may be two descriptions of the same underlying physics. This does not yet give a complete picture of a real black hole formed by a star. The best understood examples often involve idealized universes with different large-scale properties from our own. Still, they provide strong evidence that gravity, geometry, and information are closely linked. The information problem becomes especially difficult when considering what a falling observer experiences. General relativity suggests that a large horizon should be locally uneventful. Quantum arguments about information escaping can appear to require something happening near the horizon that changes the state of falling matter. One proposal suggested that an energetic barrier called a firewall might form at or near the horizon, destroying anything that crosses. This would preserve certain principles of quantum theory but violate the expectation from relativity that the horizon of a large black hole is locally smooth. The proposal caused intense debate because it forced physicists to choose among principles that all seemed reliable. Perhaps the horizon is smooth. Perhaps information escapes. Perhaps quantum entanglement behaves differently than expected. Keeping every assumption at once appears difficult. There is still no universally accepted final resolution. That uncertainty is useful for our question because it identifies an edge. Black holes do not merely create strong gravity. They bring our best theories into direct conflict over what space-time, information, and observation really mean. The center creates an even more obvious problem. Classical relativity predicts a singularity. For a simple non-rotating black hole, the singularity is often pictured as a point. For an ideal rotating black hole, the mathematics produces a ring-shaped structure and allows more complicated internal regions. Real black holes are formed through collapse and interact with their surroundings. Small disturbances may make the ideal internal picture unstable. The exact geometry inside a realistic rotating black hole is likely more complicated than the clean textbook solution suggests. What remains difficult to avoid in classical relativity is the conclusion that collapse leads to incomplete paths. An observer can reach a limit after a finite amount of personal time with no ordinary continuation provided by the theory. This is a more careful way to describe a singularity than simply saying that density becomes infinite. The singularity is not treated as an ordinary location sitting inside space-time. It is better understood as a boundary where the description ends. Asking what happens after reaching it may be like asking what lies north of the North Pole. Though the comparison is imperfect, the question may assume a continuation that the geometry does not provide. If quantum gravity replaces the singularity, then space-time may continue in a new form. The central region might contain a highly compressed quantum state. It might undergo a transition. It might connect to another region. It might avoid the classical end without resembling any familiar place. One family of ideas treats space-time as built from discrete elements. In that case, there may be a smallest scale beyond which further compression has no ordinary meaning. Collapse could reach a state where quantum properties of geometry resist the classical singularity. Another approach treats the basic ingredients as extended objects rather than points. Their behavior may smooth out interactions that would otherwise become unbounded. Black holes in such theories can have microscopic descriptions involving large numbers of quantum states. Some proposals replace the traditional interior with a complex structure extending nearly to the horizon. Instead of empty space surrounding a central singularity, the black hole could be a compact quantum object whose many possible internal arrangements account for its entropy. Other models preserve a recognizable interior for a long time but alter the final stage. There may be a bounce into an expanding region, though whether that region remains connected to our universe is uncertain. There may be a transition into something resembling a white hole after an extremely long delay. A white hole is the time-reversed mathematical partner of a black hole. Matter and light can leave it but cannot enter from outside. No confirmed white holes have been observed. Their stability and formation are serious problems, so they remain speculative. Wormholes also appear in discussions of black hole interiors. Certain ideal solutions can connect distant regions of spacetime through a bridge. The bridge in the simplest black hole solution closes too quickly to allow travel. It is not a practical tunnel and cannot be crossed from one exterior region to another. Rotating black hole solutions contain more complicated routes on paper, but the internal regions may be unstable. Radiation and small disturbances can grow dramatically near inner horizons, likely changing the geometry before any traveler enjoys the advertised shortcut. This is a recurring lesson in theoretical physics. A solution can be mathematically allowed under perfect conditions while becoming impossible once the slightest realistic disturbance is included. A perfectly balanced pencil can stand on its point in an equation. The difficulty begins when the universe remembers that small vibrations exist. The edges of black holes therefore come in several forms. The event horizon is an edge of communication. The singularity is an edge of the classical space-time description. The information problem is an edge between relativity and quantum theory. The final stage of evaporation is an edge of current prediction. None of these proves that space-time can be torn open by a large enough force. Instead, they show that extreme curvature exposes hidden assumptions in our theories. Smooth geometry may not remain fundamental. Local information may be related to distant boundaries. Space and time may emerge from quantum relationships that do not resemble either one. Black hole mergers give us a way to study some of these ideas from outside the horizon. When two black holes orbit each other, the geometry around them changes continuously. They emit gravitational waves and lose orbital energy. The orbit shrinks, the speed increases, and the waves grow stronger. During the final merger, the horizons distort and combine. The result is a single black hole that initially has an uneven shape. It settles by radiating gravitational waves in a pattern called ring-down. The frequencies and decay of that signal reveal the mass and rotation of the final black hole. The event is one of the most violent processes in the universe. Several times the mass of the sun can be converted into gravitational wave energy over a very short interval, yet the result is not a shattered space-time. The geometry absorbs the disturbance, reorganizes, and settles into a stable black hole. Computer simulations are required to follow this process because the gravitational fields are highly dynamic and strongly curved. Decades of work were needed before stable merger simulations became possible. These simulations predicted the signals that detectors later observed. The agreement between theory and measurement showed that general relativity continues working under conditions far more extreme than those found in the solar system. That success makes the remaining failure even more interesting. The theory can describe two horizons colliding and joining. It can describe the waves leaving the system. It can describe the final black hole ringing down. But it still predicts hidden singularities and cannot explain the complete quantum fate of information. A merger also demonstrates that horizons are not fixed shells. They can grow, distort, and combine. The total horizon area increases during the classical process. This behavior resembles the increase of entropy and thermodynamics and helped lead to the idea that black holes possess temperature and entropy. The comparison became more than a loose analogy once Hawking radiation was discovered. Theoretically, black holes obey laws closely related to the laws of thermodynamics. Their horizons have temperature, their area is connected with entropy, They exchange energy with their surroundings. This means a black hole is not only a gravitational object, it is also a thermodynamic and quantum system. Any complete description must combine all three areas of physics. That combination is exactly what current theories struggle to provide. General relativity describes the large-scale geometry. Quantum field theory describes particles and fields near the horizon. Thermodynamics describes the statistical behavior. A theory of quantum gravity must explain why these descriptions fit together and what microscopic structures produce them. The phrase edge of breaking is therefore appropriate, provided we are careful about what is breaking. The horizon does not appear to break. Space-time outside remains smooth. Mergers proceed predictably. The strain falls on the theories when they are asked to describe the center, the information, and the smaller scales. Perhaps space-time continues all the way inward and undergoes a quantum correction near the center. Perhaps the inside is encoded on the horizon. Perhaps the familiar interior is an approximate description that emerges only for certain observers. Perhaps space and time stop being meaningful before the classical singularity is reached. Each possibility changes the answer to our original question. If space-time is fundamental and continuous, breaking it might require creating a true boundary or singularity. If it is discrete, extreme energy may disrupt its smallest units. If it is emergent, it may dissolve when the underlying quantum relationships change. Black holes place all of these options close together. They are observable objects with measurable masses, spins, disks, jets, and gravitational waves. They are also laboratories containing inaccessible regions where known theories lose agreement. The next clue does not come from staring only into the darkness. It comes from the disturbances black holes send outward. Gravitational waves allow the universe to report how space-time behaves during collisions, collapse, and rapid motion. They show how much distortion the geometry can carry without failing, and how the effects of cosmic violence can travel across vast distances before producing a movement smaller than an atomic nucleus inside a detector on Earth. That tiny movement is the key to one of the most direct ways we can study space-time under extreme conditions. Gravitational waves do not show us space-time as a visible surface, and they do not allow us to watch a black hole from the inside. What they provide is a record of how the geometry changes when massive objects move violently. A pair of black holes can collide far beyond the reach of any telescope, and the resulting disturbance can travel across the universe until it reaches Earth and changes the distance between two mirrors by an almost impossibly small amount. The event that produced the signal may have involved masses greater than the Sun, moving at a significant fraction of the speed of light. The effect measured on Earth can be smaller than the width of a proton. That contrast is one of the reasons gravitational wave astronomy is so remarkable. The source can be among the most powerful events in existence, while the arriving signal is so weak that a passing truck, a gust of wind, or a person walking through the wrong part of a building can create a much larger disturbance. To understand where these waves come from, begin with a simple orbit. Earth moves around the Sun, and the Sun moves slightly in response to Earth. Both objects travel through space-time, and their motion changes the gravitational field around them. In principle, this system produces gravitational waves. The effect is far too weak to matter for the orbit over ordinary timescales, and far too small for current detectors to measure directly. The weakness comes partly from the fact that gravity itself is weak compared with the other fundamental interactions, and partly from the smoothness of the motion. Earth and the Sun are massive by human standards, but they are not compact enough, close enough, or fast enough to create a strong signal. Replace them with two neutron stars or two black holes, and the situation changes. These objects can contain enormous mass within very small regions. They can orbit close together without touching in the ordinary sense. As they lose energy through gravitational waves, they move inward and accelerate. The changing geometry becomes more rapid, and the waves become stronger. The waves do not come from a mass simply existing. A perfectly still, isolated object creates a gravitational field, but it does not send out a continuous gravitational wave. Even steady motion in a straight line is not enough. The important requirement is changing motion arranged in an uneven way. A perfectly spherical star that expands and contracts equally in every direction would not produce the same kind of outgoing gravitational wave. Its gravitational influence changes, but the symmetry prevents the required pattern from escaping as radiation. Something must create an imbalance. Two objects orbiting one another do this naturally. A lopsided stellar explosion may do it. A spinning neutron star with a small deformation can do it. A rapidly changing distribution of mass creates the moving pattern that travels outward. The wave stretches space-time in one direction while squeezing it in another. A moment later, those effects reverse. Imagine a circle of freely floating particles in space. As a gravitational wave passes through them, the circle becomes slightly stretched into an oval. Then it returns toward a circle and stretches in the other direction. The particles are not being pushed through a fixed background in the ordinary sense. The measured separations between them are changing because the geometry changes. This is why the word ripple is useful but incomplete. A ripple on water changes the height of the water surface. A gravitational wave changes relationships of distance and time. It does not require a material medium. It travels through empty space because it is a disturbance of space-time itself. The waves move at the speed of light. This was predicted by general relativity and confirmed through observations. When two neutron stars merged, astronomers detected both gravitational waves and light from the event. The signals reached Earth after traveling for an immense amount of time, with their arrival showing that the two forms of radiation moved at essentially the same speed within very strict limits. That observation did more than confirm a basic prediction. It ruled out many alternative theories of gravity that allowed gravitational disturbances to travel at a noticeably different rate. One distant collision gave researchers information about gravity, neutron stars, heavy elements, and the expansion of the universe. Before direct detection became possible, the best evidence for gravitational waves came from a pair of neutron stars. One of them was a pulsar, sending out regular radio pulses like a precise cosmic beacon. Astronomers tracked the orbit and found that the two stars were gradually moving closer together. The amount of orbital energy being lost matched the amount general relativity predicted should be carried away by gravitational waves. The waves themselves were not detected at Earth, but their effect on the orbit was clear. It was similar to noticing that a battery is losing charge and correctly identifying the device using the energy even though you cannot yet see the current directly. Direct detection required a different approach. The main instruments use long arms arranged at right angles. A laser beam is split and sent along both arms. Mirrors reflect the light back, and the returning beams are compared. Under ordinary conditions, the paths are arranged so that the light produces a stable pattern. When a gravitational wave passes, one arm becomes slightly longer while the other becomes slightly shorter. The difference changes the way the light combines, creating a measurable signal. Saying that an arm becomes longer can be confusing because the mirrors are not simply dragged apart through a rigid space. The geometry between them changes. The light traveling along the arm also experiences that geometry. The detector is designed so that the combined effect leaves a pattern researchers can measure. The change is extraordinarily small. The arms are several kilometers long, but the shift can be far smaller than an atomic nucleus. Detecting it requires the mirrors to be isolated from ground vibrations, temperature changes, sound, electrical noise, and many other disturbances. The mirrors hang from complex suspension systems. The laser must remain stable. The tubes carrying the light are kept under extreme vacuum so the air molecules do not interfere. The detector records a continuous mixture of useful data and unwanted noise. One instrument alone would struggle to prove that a brief signal came from space. A local disturbance could imitate part of the pattern. This is why several detectors are used in different locations. A true gravitational wave reaches them at slightly different times with a related signal shape. Comparing the arrival times also helps estimate the direction of the source. The first direct detection came from two black holes merging. The recorded signal lasted only a fraction of a second in the detector's most sensitive range, but it contained a clear progression. The frequency rose as the black holes spiraled closer. The signal became stronger. Then the objects merged, followed by the fading vibration of the final black hole settling down. This rising pattern is often called a chirp because when converted into sound, it resembles a short increase in pitch. The actual gravitational wave is not sound. Space is too empty for an ordinary sound wave to travel between galaxies. Researchers turn the data into audio because the frequencies can fall within the range of human hearing and because our ears are good at noticing patterns. The signal carried enough information to estimate the masses of the original black holes. the mass of the final black hole, its rotation, and the distance to the event. It also showed that part of the system's mass had been converted into gravitational wave energy. For a brief moment, the power carried by the waves was greater than the combined light output of the visible stars in the observable universe. This statement sounds as though the wave should have arrived with enough force to knock planets out of orbit. It did not. The energy spread outward across an ever-growing region. By the time it reached Earth, the effect was extremely weak. Energy can be enormous at the source and negligible at a distant location. A bright lamp is easy to see nearby and difficult to notice from many kilometers away. A gravitational wave spreads through three-dimensional space, weakening with distance as it covers a larger area. The first detections also revealed something unexpected about black holes. Before gravitational wave astronomy, confirmed stellar black holes were often found by watching them interact with companion stars. Those observations suggested a certain range of masses. The first merging black holes were heavier than many astronomers expected. This showed that the universe could produce pairs of heavy black holes and bring them close enough to merge. Researchers then had to consider how these systems formed. They may begin as pairs of massive stars that evolve together. They may form separately in dense star clusters and later become partners through gravitational encounters. Different detected systems may come from different roots. Each merger adds information about the population. The masses, spins, distances, and orientations help researchers test models of stellar evolution. The signal is not only a test of spacetime, it is also a record of how stars lived and died. Neutron star mergers produce a richer collection of signals because neutron stars contain matter and can emit light. When two approach each other, they create gravitational waves in the same broad way as black holes. During the final moments, the stars can deform under each other's gravity. Their internal structure affects how easily they deform. A more compact neutron star responds differently from one with a slightly larger radius. Those differences leave subtle marks in the gravitational wave signal. By studying them, physicists can learn about matter at densities far beyond ordinary atomic nuclei. The collision can produce a temporary massive neutron star or collapse quickly into a black hole. It can throw neutron-rich material into space. Nuclear reactions in that expanding debris create heavy elements, including some of the gold and platinum found in the universe. Light from the heated material can be observed across several wavelengths. Telescopes can follow the changing brightness and color. At the same time, gravitational waves reveal the motion of the compact objects before and during the collision. This combination is called multi-messenger astronomy. Different signals describe different parts of the same event. Light shows hot matter and nuclear processes. Gravitational waves show the changing motion and geometry. Neutrinos may provide another view in some explosions. Using them together produces a more complete account than any one signal could provide alone. A supernova within our galaxy could also produce gravitational waves if the collapse is uneven enough. The signal would reveal motion deep inside the star, reaching us from regions hidden from light. Neutrinos would escape from the core as well, while visible light might arrive later after the shock reaches the surface. Such an event could allow astronomers to compare the collapse through several channels. The difficulty is that supernovae close enough for detailed gravitational wave detection are rare. Astronomy sometimes requires instruments to remain prepared for an event that may not occur during the working life of the people who built them. Rapidly rotating neutron stars may create longer-lasting signals. If the star has a tiny mountain or any other slight departure from perfect symmetry, its rotation can produce continuous gravitational waves. The mountain need not resemble a mountain on Earth. A deformation far smaller than the thickness of a sheet of paper could matter because the star is so dense and rotates so quickly. Detecting such a signal requires combining data over long periods. The signal may remain weak but regular. Researchers must account for changes in the star's rotation, the movement of Earth, and the detector's orientation. There may also be a background made from many unresolved gravitational wave sources. Instead of identifying each one, detectors would measure a general hum. Some of this background may come from pairs of supermassive black holes slowly orbiting in distant galaxies. These waves have much lower frequencies than those detected by ground-based instruments. Measuring them requires a different method. Astronomers use pulsars spread across the galaxy as a natural network of clocks. A passing gravitational wave slightly changes the arrival times of their radio pulses. By watching many pulsars for years, Researchers can look for a shared pattern in the timing changes. Evidence for such a background has begun to emerge. It suggests that many supermassive black hole pairs are contributing to a low-frequency gravitational murmur across the universe. Future space-based detectors will target frequencies between the ranges studied by ground detectors and pulsar timing. Instead of mirrors connected by tubes on Earth, spacecraft will exchange laser signals across millions of kilometers. A space detector will avoid much of the vibration caused by the ground and will use much longer arms. It should detect mergers involving massive black holes, compact stars slowly falling into larger black holes, and many close binary stars within our galaxy. A small compact object orbiting a massive black hole can trace the geometry with great precision. Each orbit samples the curvature. The resulting gravitational waves contain a detailed record of the black hole spacetime. If the measured signal differs from the prediction of general relativity, it could reveal new physics. So far, observations have been consistent with relativity. The waves travel at the expected speed. Their shapes match simulations. The ring-down signals agree with black holes having the properties predicted by the theory. Scientists continue searching for small disagreements. They compare whether different parts of a signal give the same final mass and rotation. They look for unexpected additional wave patterns. They test whether the signal loses strength or changes frequency in an unusual way during travel. Even a tiny deviation could matter. It might indicate an additional field, an altered theory of gravity, an unexpected property of black holes, or a failure in the assumptions used to model the source. More often, an apparent deviation turns out to be noise, incomplete modeling, or an instrument effect. Physics is full of exciting possibilities that later reveal themselves to be a cable behaving badly. Gravitational waves also provide a direct answer to one part of our central question. Spacetime can be disturbed by enormous events without tearing. Two black holes can merge. Neutron stars can collide. A stellar core can collapse. The geometry carries the disturbance away in a controlled form. The wave can stretch and squeeze distances, but it does not leave a permanent gap behind. After it passes, objects return close to their previous arrangement. Although some waves can produce a lasting change called gravitational memory, this effect shifts the relative positions or motion of objects slightly after the wave has gone. Memory does not mean spacetime has been damaged. It means the event has left a permanent geometric record. The universe does not always return exactly to its earlier arrangement after a burst of radiation. The effect is expected to be very small and difficult to detect. Future instruments may measure it. Doing so would provide another test of how gravity behaves during highly energetic events. Could a gravitational wave ever be strong enough to destroy an object? Very close to a violent source, changing tidal forces could be severe. A powerful wave could stretch and compress matter. The object would break because its internal forces could not maintain its shape. Spacetime itself would still be behaving according to general relativity. The wave would not be a crack. It would be an extreme but permitted change in curvature. Could two gravitational waves collide and create a black hole? In principle, energy gravitates, including the energy carried by gravitational waves. If enough energy were concentrated within a small enough region, it could contribute to horizon formation. Creating such a condition deliberately is far beyond any realistic technology. The important point is that gravity can act on gravity. Gravitational waves carry energy, and that energy influences space-time. The theory is nonlinear, meaning the waves do not always pass through one another as though completely independent. Under ordinary detected conditions, the interactions are extremely weak, but under extreme conditions, they can matter. This nonlinear behavior is one reason black hole mergers require powerful computer simulations. The geometry affects the motion of the black holes. Their motion changes the geometry. The changing geometry carries energy away, altering the orbit again. Every part of the process responds to the others. During the final moments, space-time is not a calm stage with objects moving across it. The stage and the objects form one changing system. Horizons bend, merge, and settle. Waves leave the region. The final geometry contains less mass than the original total because energy has escaped. Even this violent process remains predictable. The theory does not produce a random tier or a region where distances lose all meaning outside the horizons. The signal observed far away follows a structured pattern. This is strong evidence that space-time can tolerate severe motion and curvature. There is a limit to what gravitational wave observations can tell us. They mainly reveal the exterior dynamics. The waves produced during a merger come from the changing geometry around the horizons. They do not carry direct reports from the singularities. The final ringdown tests the outer structure of the resulting black hole. If the object has a horizon and an exterior matching relativity, the signal behaves in a particular way. A different type of compact object with a surface close to where the horizon would be might produce additional signals or echoes. Researchers have searched for such echoes. No conclusive evidence has shown that ordinary black holes possess reflective surfaces outside their expected horizons. The data continues to improve, and future detectors will make stricter tests possible. The lack of a visible failure is itself informative. Nature can produce collisions involving compact masses, high speeds, and rapid changes in curvature while preserving the smooth exterior space-time description. Whatever breaks our theories must lie at more extreme scales or in regions hidden from direct observation. Gravitational waves bring us close to that boundary without crossing it. They confirm that dynamic space-time is real. It can carry energy, it can react to motion, it can ring after a collision, it can preserve a detailed record of events that happened billions of years ago. They also show why the phrase force needed to break space-time may be asking for the wrong measurement. The strongest detected events do not break it. They generate larger curvature and stronger waves. The framework continues to respond. To find a possible point where smooth geometry truly stops working, increasing the violence of an ordinary event may not be enough. The important change may occur when distances become so small and energy becomes so concentrated that quantum effects cannot be ignored. At that scale, the question is no longer how hard space-time can be shaken. It becomes whether space-time still exists as a smooth thing that can shake it all. That takes us away from waves crossing galaxies and toward the smallest length and shortest duration that current physics can meaningfully discuss, where the familiar geometry may begin to lose its continuous form. That smallest scale is known as the Planck scale, and it marks the point where our usual descriptions of space, time, matter, and gravity can no longer be trusted separately. It is not a physical border floating somewhere in the universe. There is no sign beside a black hole saying that ordinary physics ends here. The Planck scale is a range of extremely small distances, short durations, and concentrated energies where quantum effects and gravity are expected to become equally important. In everyday situations, physicists can often choose which theory matters most. General relativity describes planets, stars, black holes, and the large-scale structure of the universe. Quantum physics describes atoms, particles, light, and the interactions taking place at very small scales. Each theory has been tested with extraordinary precision in the conditions where it is normally used. The trouble begins when a situation is both extremely small and strongly affected by gravity. A particle in a laboratory requires quantum physics, but its gravitational influence is usually too weak to matter. A planet requires gravity, but its large-scale motion does not require a detailed quantum description. Near the classical center of a black hole, both theories are needed at the same time. The same is true when we try to describe the earliest stage of the universe. General relativity treats space-time as a smooth geometry. A location can be divided into smaller locations, and those smaller regions can be divided again. There is no required smallest piece in the theory. Curvature can vary continuously from one point to the next. Quantum physics gives a different kind of picture. It does not always assign objects one exact position or one definite state before a measurement. Physical quantities fluctuate. Particles can behave like waves. Empty space is not completely empty. Fields remain active even when no ordinary particles are present. If space-time itself must obey quantum rules, then its geometry may also fluctuate. Distances may not remain perfectly defined. Time intervals may become uncertain. The difference between one possible shape of space-time and another may become impossible to ignore. At large scales, these fluctuations would be extremely small. A room does not visibly change shape because the geometry is exploring several quantum possibilities. A clock on the wall does not lose track of the order of events. The collective effect settles into the smooth space-time described by relativity. At the Planck scale, the fluctuations may become as important as the geometry being measured. Trying to define a precise distance could disturb the region so strongly that the original idea of distance stops working. The smooth background assumed by ordinary physics may no longer exist. The Planck length is far smaller than an atomic nucleus. It is smaller than the distances explored by the most powerful particle accelerators by an enormous margin. Even a proton is vast compared with it. If a proton were expanded until it was comparable to the observable universe, the Planck length would still correspond to something very small by human standards. This comparison is not exact, but it gives a sense of the gap. The Planck scale is not merely a little beyond current microscopes. It is separated from present experiments by an almost unimaginable range. The Planck time is the duration light would take to cross the Planck length. It is an extremely short interval. Our most precise clocks do not come close to resolving it. Even the fastest known physical processes take vastly longer. These scales are not chosen because they form attractive round numbers. They arise when several basic features of physics are combined: gravity, quantum behavior, and the speed at which information travels. The result indicates where no single existing theory can be ignored. Suppose we try to examine a smaller and smaller region. To see fine detail, we need radiation or particles with shorter wavelengths. Shorter wavelengths require greater energy. This works well through ordinary microscopy and particle physics. Increasing the energy allows us to probe smaller structures. Eventually, concentrating enough energy into a small enough region creates a new problem. Energy contributes to gravity. Pack too much energy into too little space, and the region may form a black hole. The very attempt to inspect the smallest distance could hide that distance behind a horizon. Instead of revealing finer detail, the experiment would create an object that prevents information from escaping. Nature may therefore impose a limit. Not because our instruments are poorly designed, but because measurement itself changes the geometry. This is sometimes presented as evidence that there must be a smallest meaningful length. That conclusion is plausible, but it is not proven in one universally accepted way. Different approaches to quantum gravity describe the limit differently. The main lesson is that ordinary measurement cannot be separated from gravity at sufficiently high energy. A microscope works by interacting with the object being studied. At normal scales, the disturbance can be controlled. At the Planck scale, the energy needed for the interaction may alter spacetime so severely that the original target is no longer available. This is one reason building a more powerful accelerator is not a straightforward path to the Planck scale. Current accelerators already require enormous machines to reach the highest controlled particle energies. Reaching the Planck range directly would require technology far beyond anything available. Even if such energy could be produced, concentrating and controlling it would raise severe gravitational problems. The accelerator might become less of a microscope and more of an expensive attempt to create a very small black hole. Some theories involving additional dimensions suggest that gravity could become strong at lower energies than the usual Planck estimate. These ideas led to speculation that tiny black holes might be produced in particle collisions. Experiments have not found evidence for such objects, and the simplest versions of those proposals face strict limits. If microscopic black holes could form, they would be expected to evaporate quickly through quantum effects rather than grow by consuming the planet. Cosmic rays have struck Earth and other astronomical bodies at high energies for billions of years without causing such disasters. Nature has already performed many collision experiments without asking for a safety meeting. Directly reaching the Planck scale may be unrealistic, but indirect evidence could still reveal the correct theory. Physics often studies inaccessible conditions by observing their consequences. No one enters the core of a star, yet its light and vibrations reveal what happens inside. No detector crosses a black hole horizon and returns, yet motion and radiation outside provide information about the object. Quantum gravity may leave small traces in the early universe: black hole behavior, gravitational waves, particle interactions, or the large-scale structure of the cosmos. The challenge is separating those traces from ordinary effects and from the many theoretical possibilities. One approach to quantum gravity is string theory. In its basic picture, the fundamental objects are not dimensionless points. They are extremely small, extended structures that can vibrate in different ways. Different vibration patterns appear as different particles. This extension can soften some of the problems that appear when particles interact at a single exact point. Gravity arises naturally within the theory because one of the possible vibrations behaves like the quantum carrier expected for gravity. String theory also requires additional spatial dimensions in its most familiar forms. These dimensions would be hidden or compact at scales too small to observe directly. The theory has developed into a large framework connecting gravity, particle physics, black holes, and quantum information. It has produced important mathematical results and useful insights into black hole entropy. It has also shown examples where a gravitational theory in one region is equivalent to a quantum theory without gravity on a boundary. What it has not yet produced is a unique confirmed description of our universe. There are many possible ways the additional dimensions could be arranged, leading to many possible low-energy worlds. Finding clear experimental evidence remains difficult. Another approach is loop quantum gravity. It begins by applying quantum principles directly to geometry. In this picture, areas and volumes may come in discrete units. Space-time at the smallest scale is not smooth, but built from a network of quantum relationships. The network is not sitting inside an already existing space. Its connections help define space itself. Large, smooth geometry emerges when many of these quantum elements are considered together. This is similar to how a smooth surface can emerge from a huge collection of atoms. A table feels continuous to a hand even though matter is made from smaller parts. Space-time might appear continuous because its fundamental units are far below any scale we can normally detect. Loop-based models can replace some classical singularities with quantum transitions. In certain descriptions of the early universe, the Big Bang singularity becomes a bounce from an earlier contracting state. In models of black holes, the central collapse may also be halted or redirected by quantum geometry. These results depend on assumptions and simplified settings. They do not yet provide a complete confirmed account of realistic stars collapsing into black holes. Still, they demonstrate how a discrete space-time might avoid the infinities of classical relativity. Other approaches treat space-time as emerging from more basic quantum information. Distance may reflect how strongly different parts of a quantum system are connected. Nearby regions would share more direct relationships, while distant regions would be less closely linked. Entanglement becomes especially important in these ideas. Two quantum systems can share a state in a way that cannot be described as two independent objects carrying separate information. Measurements show correlations that remain even when the systems are far apart. Some theoretical work suggests that the pattern of entanglement helps construct a smooth geometry. Reduce or remove particular connections, and the corresponding space-time may separate or change shape. This offers a new way to think about breaking space-time. A tear might not require ripping a material surface. It could mean disrupting the quantum connections that allow two regions to behave as parts of one continuous geometry. In certain simplified models, reducing entanglement between two sets of quantum degrees of freedom causes the geometric connection between them to narrow. Remove enough of it, and the space-time description divides into separate regions. That does not mean a person could cut space-time using a machine that switches off entanglement. The examples are theoretical and often involve highly controlled mathematical systems. They show that geometry may be related to information more deeply than everyday experience suggests. Another possibility is that space-time resembles a material with different phases. Water can be solid, liquid, or gas without changing the basic type of molecule. A fundamental quantum system might produce smooth space-time in one phase and something with no ordinary geometry in another. Under moderate conditions, the space-time phase would support familiar distances, directions, and causal order. Under extreme energy or temperature, it might enter a different state where those ideas no longer apply. The earliest universe may have passed through such a transition. Asking what happened before ordinary space-time emerged could be difficult because the word before assumes that time already existed. This does not automatically make the question meaningless. A deeper theory might contain an ordering concept that later becomes time. It may describe relationships between states without using the same clock-based structure we experience. The situation is similar to asking for the temperature of one isolated molecule. Temperature is useful for a large collection of particles, but it does not apply to a single molecule in the same way. If time is emergent, demanding an ordinary time coordinate at the deepest level may be asking for a large-scale property where it does not belong. The Planck scale is often described using the phrase quantum foam. The image suggests that space-time at tiny scales may fluctuate violently, with geometry changing from moment to moment. Small tunnels or disconnected structures might appear and disappear. This picture came from attempts to imagine quantum fluctuations in geometry. It should not be taken as a confirmed microscopic photograph. We do not know that space-time literally resembles foam, and there is no evidence of tiny bubbles floating beneath ordinary reality. The useful point is that smooth geometry may become unreliable. If every possible shape contributes to the quantum state, then space-time may not have one definite structure until viewed at a larger scale. The uncertainty could affect the order of events. At ordinary scales, one event can cause another if a signal has time to travel between them. The causal structure is clear enough to prevent effects from arriving before their causes. At the Planck scale, fluctuating geometry could make these relationships less definite. The idea of one event being strictly before another might become approximate. A complete theory would still need to explain why ordinary cause and effect emerge so reliably at larger scales. Some proposals preserve a fundamental causal order. Causal set theory, for example, treats space-time as a collection of discrete events connected by relations that say which events can influence which others. The smooth dimensions we observe would emerge from a very large set of these basic connections. In such a model, the number of fundamental events corresponds roughly to space-time volume. Geometry becomes statistical, much as pressure emerges from the collective collisions of particles in a gas. Other approaches build space-time from simple geometric pieces. These pieces are combined in many possible ways, and a smooth, large-scale universe can emerge from the collective behavior. The goal is to recover general relativity without assuming smooth space-time from the beginning. Each approach makes a different choice about what is fundamental. Strings make extended quantum objects fundamental. Loop-based theories make quantum geometry central. Causal sets begin with events and their ordering. Information-based approaches focus on quantum relationships. Other models use fields, matrices, networks, or more unfamiliar structures. The number of ideas reflects both the importance and difficulty of the problem. Experiments have not yet forced physicists toward one final theory. Many proposals can match known physics at accessible scales, which is necessary but not enough. A successful theory of quantum gravity must reproduce the tested predictions of general relativity when curvature is moderate and distances are large. It must also agree with quantum physics where gravity is weak. It should explain black hole entropy, avoid or interpret singularities, and describe the early universe without relying on undefined conditions. It should ideally make predictions that can be tested. A theory that explains everything only at unreachable energies risks becoming difficult to distinguish from its competitors. Researchers therefore search for amplification. A tiny quantum gravity effect may accumulate over a long distance or appear in a highly sensitive system. Light traveling from a distant explosion could reveal whether space-time causes different energies to move at slightly different speeds. Observations have placed strict limits on many such effects. High-energy photons from distant sources arrive with no clear Planck scale delay of the type predicted by some models. This does not rule out quantum gravity. It rules out or constrains specific ways the effect might appear. The polarization of ancient light can also test whether space-time has small directional or energy-dependent properties. Again, observations show that ordinary relativity works extremely well. Any underlying granularity must preserve smooth behavior with remarkable accuracy at larger scales. Gravitational waves offer another possibility. If space-time has a microscopic structure, waves might disperse, lose energy, or develop additional patterns while traveling. Current observations show no convincing departure from general relativity, but future detectors will examine longer signals and broader frequency ranges. The early universe may provide the strongest natural experiment. During its first moments, energy densities were far greater than anything humans can create. Quantum fluctuations were stretched to astronomical scales by cosmic expansion and may have left patterns in the distribution of matter and ancient radiation. Measurements of those patterns already support the idea that tiny early fluctuations became the seeds of galaxies. More detailed observations may reveal whether gravity itself had quantum fluctuations and how they behaved. A particular pattern in ancient background radiation could provide evidence of primordial gravitational waves. Detecting it would offer information about very high energy conditions in the early universe. The search is difficult because dust in our galaxy and other effects can imitate parts of the signal. Black holes remain another major testing ground. Their temperature and entropy connect quantum theory, gravity, and thermodynamics. Any proposed theory must explain why horizon area behaves like a measure of hidden microscopic information. Some approaches count the possible quantum states that correspond to a black hole with given visible properties. In special cases, the calculation matches the entropy predicted through gravity. This is important because it suggests that black holes are not featureless objects at the deepest level. They possess many microscopic arrangements. Even though an outside observer sees only mass, rotation, and charge, those microscopic states may explain how information is preserved during evaporation. The outgoing radiation could contain subtle correlations that appear only when the full quantum process is considered. If that is correct, the smooth horizon and interior described by relativity may be approximate features. They work for large black holes and ordinary observers, but the complete quantum state contains more information than the classical geometry reveals. The Planck scale would then be the level where the hidden description becomes unavoidable. It is where space-time stops being a sufficient starting point and becomes something that must be explained. This changes our original question again. Asking how much force would break space-time assumes that space-time is a substance already present. At the Planck scale, force may not be the most basic concept. Force requires objects, positions, changes in motion and time. If those ideas emerge from deeper physics, then the question must be translated into the language of the underlying theory. We might instead ask how much energy must be concentrated before smooth geometry fails. We might ask what conditions destroy the connections that produce distance. We might ask whether a region can undergo a phase transition into a state without ordinary space and time. None of these questions currently has one confirmed numerical answer. There is a natural energy scale associated with quantum gravity, but reaching it does not guarantee a simple event where space-time cracks. The outcome could depend on the distribution of energy, the quantum state, the surrounding geometry, and the theory that ultimately proves correct. A single particle carrying enormous energy does not necessarily create the same situation as the same energy compressed and trapped in a small region. Two particles passing through one another differ from a stable concentration. A black hole spreads its mass behind a horizon whose size depends on that mass. The arrangement matters, just as it did for stars. Total energy alone is not enough. Density, motion, symmetry, pressure, and quantum state all contribute. There may also be a limit on how much information can fit inside a region without forming a black hole. The connection between horizon area and entropy suggests that nature restricts information storage more severely than ordinary volume-based reasoning would imply. If too much energy or information is packed into a region, the region may respond by forming a horizon. The black hole then hides the attempted overloading behind a boundary. This has led some physicists to view black holes as nature enforcing a limit on what can be resolved or stored locally. From that perspective, space-time protects itself from direct probing. Push too hard at a small distance and the experiment produces a horizon. The hidden region may contain quantum gravity, but the observer remains outside with only indirect evidence. This does not mean the Planck scale is forever inaccessible. The universe has already created the relevant conditions. They may exist inside black holes and may have existed during the earliest cosmic period. The problem is finding signals that survive and reach us. A correct theory might predict features of black hole mergers, evaporation, early cosmic structure, or particle behavior that no competing theory can reproduce. One reliable discrepancy could provide the opening physicists need. For now, the Planck scale remains a warning label attached to our calculations. Below this range, smooth spacetime may not be meaningful. Near this range, infinities in classical relativity cannot be accepted without a quantum correction. Concepts that seem basic may become approximations. Space could be discrete, time could be emergent, geometry could arise from entanglement, singularities could become transitions, black hole interiors could be encoded in information stored in an unexpected way. Each option would replace the image of a torn sheet with something more complicated. The word fray is therefore more suitable than break. Our theories begin to fray because their assumptions pull in different directions. Relativity assumes a smooth geometry. Quantum physics requires fluctuations and uncertainty. Applying both without a deeper framework produces contradictions or uncontrolled infinities. The physical universe does not necessarily fray with them. Nature continues doing whatever it does. It is our description that loses clarity. That distinction has appeared several times. A singularity might be a failure of spacetime, or it might be a failure of general relativity. A horizon might hide a true endpoint, or it might hide a quantum state that remains finite. The absence of a complete theory prevents us from deciding. The final answer must therefore separate what is measured from what is inferred. We know that spacetime bends. We know that clocks respond to gravity. We know that gravitational waves carry energy. We know that black holes form and merge. We know that quantum physics governs microscopic systems. We do not know whether spacetime has fundamental pieces. We do not know exactly what replaces a black hole singularity. We do not know whether time exists at the deepest level. We do not know whether a geometric connection can be destroyed in a physically realizable process. Those uncertainties do not make the question useless. They show exactly where the frontier lies. The force required to break spacetime may not be a force at all. The closest known threshold is the concentration of energy where quantum gravity takes control and smooth geometry can no longer be assumed. Whether that transition creates a boundary, a bounce, a new phase, a hidden network, or no spacetime in the familiar sense remains open. To finish the journey, we need to gather the different meanings of breaking and decide which of them nature clearly allows, which remain mathematical possibilities, and which may only reflect the limits of the language we use to describe the universe. After following gravity from planets to stars, from collapsing cores to black holes, and from gravitational waves to the Planck scale, we can finally return to the question that started this journey: can spacetime truly break? The most honest answer is that we do not yet know. Physics gives us several situations that resemble breaking, but none of them can be confirmed as a literal tear in spacetime. Some are changes in geometry, some are boundaries that prevent information from escaping, some are places where our equations stop working. Others are theoretical possibilities that may never occur in the real universe. The difficulty begins with the word break. A physical object breaks when the forces holding its parts together can no longer resist stress. Glass develops cracks because the bonds in the material fail. Metal bends and eventually separates when its internal structure cannot support the applied load. A biscuit breaks because tea has quietly completed the work that gravity began. Spacetime is not known to be a material made from ordinary particles and bonds. It does not have a measured strength in the same way as steel, stone, or glass. There is no confirmed test showing that a certain amount of pressure causes it to split into pieces. This means there is no accepted value for the force needed to break spacetime. What physics can describe is curvature. Matter and energy alter the geometry of space and time. A small amount creates a small effect. A large concentration creates a stronger effect. Planets curve spacetime enough to hold moons in orbit. Stars curve it enough to guide planets and bend light. Neutron stars create far stronger curvature. Black holes create regions where escape becomes impossible. None of these examples require spacetime to tear. A black hole is often treated as the clearest candidate for broken spacetime. But the event horizon itself is not a crack. It is a boundary separating events that can still communicate with the outside universe from events that cannot. An object can cross the horizon without striking a surface. For a sufficiently large black hole, it may cross without feeling anything sudden at that exact location. The geometry at the horizon can remain smooth. General relativity describes it well. The serious problem lies deeper inside, where the classical theory predicts a singularity. A singularity is often described as a point of infinite density. That description captures part of the problem but can create the wrong picture. It may sound like a tiny object sitting at the center of the black hole with an unlimited amount of matter packed into it. A more careful description is that the space-time paths in the theory become incomplete. They reach an end and the theory gives no ordinary continuation. If a falling observer reaches that end after a finite amount of personal time, space-time appears to stop providing a future path. That is much closer to what breaking might mean. The geometry no longer behaves as a complete structure. Still, The prediction comes from general relativity alone. General relativity does not include a full quantum description of gravity. Near the singularity, matter and geometry would reach conditions where quantum effects should become essential. Using the classical theory there may be like using the rules of ordinary water flow to describe individual molecules. The theory is successful at larger scales, but it may not contain the right ingredients for the smallest one. This leaves two possibilities. The singularity could represent a genuine end in space-time, or it could show where general relativity stops being reliable. Most researchers expect the second possibility. They expect a theory of quantum gravity to replace the singularity with something finite, though no confirmed theory has yet shown exactly what that replacement is. If the singularity disappears in the deeper theory, then black holes may not break space-time at all. They may push it into a state that cannot be described as a smooth geometry. The interior could contain a quantum region, a discrete structure, a transition, or a new form of connection. The familiar idea of location may stop applying without reality itself coming to an end. This distinction matters. A map can fail without the land failing. If a map shows no route beyond a certain point, the road may still continue. The map may be incomplete, badly drawn, or based on assumptions that do not hold in that region. Our current picture of space-time may be such a map. The same problem appears when we look backward toward the beginning of the observable universe. General relativity suggests that the universe was once much hotter and denser. Follow the classical equations far enough into the past, and they reach another singularity. This is commonly called the Big Bang singularity, but it should not be imagined as an explosion happening at one location in an already existing empty space. The early universe involved the expansion of space itself. Every region we observe today was once much closer together. The classical description eventually reaches conditions where density and curvature become unbounded. Once again, the theory stops giving a complete answer. It does not tell us whether time truly began, whether another state existed before the expansion, or whether the word before has any meaning at that level. A theory of quantum gravity might replace the beginning with a bounce from an earlier contracting state. It might describe a period with no ordinary space or time. It could show that the singular beginning is an approximation produced by extending general relativity too far. If space-time emerged during the early universe, then asking whether it broke before that moment may be the wrong question. Something cannot break before it exists in the relevant form. The deeper system might undergo a transition that produces space-time, much as cooling matter can produce a solid structure that was not present in the hotter state. This possibility changes the central problem. Instead of asking what force breaks space-time, we ask what conditions cause the smooth space-time description to disappear. The likely answer involves enormous energy concentrated within an extremely small region. The Planck scale marks the range where gravity and quantum effects can no longer be separated. At that scale, ordinary ideas of distance, duration, and position may become unreliable. Trying to inspect a smaller region requires greater energy. Concentrating that energy also increases its gravitational effect. Eventually, the measurement may create a horizon and hide the region being examined. This gives space-time an unusual kind of resistance. A physical material resists by pushing back against stress. Space-time may resist precise probing by forming a black hole. The more energy used to examine a tiny distance, the more the geometry changes. This does not prove that the Planck scale is a hard minimum length. It does show why the ordinary method of using more energy to see smaller structures cannot continue without limit. Gravity eventually becomes part of the measuring process. Could an advanced civilization gather enough energy to reach that regime deliberately? In principle, physics does not forbid concentrating very large amounts of energy. In practice, the required conditions are far beyond any technology humans possess. The energies reached by current particle accelerators are enormous compared with ordinary chemical processes. Yet they remain extremely far below the standard Planck energy. Even if the energy could be produced, controlling and compressing it would be another problem. The equipment itself would need to survive conditions that could create intense radiation, unstable matter, or a microscopic horizon. The experiment might hide its own result before any signal could escape. Nature has access to much greater scales than our laboratories. Black hole interiors, and the earliest universe are the most likely places where quantum spacetime has already existed. The problem is that these places are either hidden behind horizons or separated from us by the full history of cosmic expansion. Gravitational waves bring us close to extreme gravity, but they do not show a tear. Two black holes can merge and release a huge amount of energy. Their horizons can distort and join. The surrounding geometry can change rapidly. Waves can travel across billions of light years and carry information about the event. The exterior spacetime remains describable. The waves have a regular structure. The final black hole settles into a predictable state. General relativity continues working under conditions that would destroy any ordinary object. This tells us that spacetime can endure far more disturbance than the word fabric might suggest. It can bend, stretch, carry waves, and reorganize around merging horizons without producing an exposed crack. A sufficiently strong gravitational wave could damage matter nearby. It could stretch a planet, disrupt a star, or alter the path of light. The matter would break because its internal forces would fail. Spacetime would still be carrying the wave according to its normal rules. The same is true near a black hole. Tidal forces can pull an object apart. The closer side follows a different path from the farther side. Molecules separate, structures collapse, and eventually particles may be torn from one another. The object breaks. The geometry does not necessarily do so. A big rip, if the expansion of the universe ever developed in that direction, would also destroy structures. Galaxies could be separated. Solar systems could be pulled apart. Matter itself might eventually fail to remain bound. That scenario depends on the unknown nature of dark energy, and current evidence does not establish that such an ending will occur. Even if it did, the event would still be described as an extreme evolution of spacetime rather than a crack appearing in it. Another possible meaning of breaking involves causality. Spacetime determines which events can influence one another. Light cannot normally travel faster than the local speed limit set by relativity. Causes occur before their effects for observers following ordinary paths. Certain mathematical solutions of general relativity contain paths that return to an earlier event. These are called closed time-like curves. If they could exist physically, an observer might travel along a future directed path and arrive in their own past. This would not split space-time into visible pieces, but it would damage the ordinary order of cause and effect. A person could influence the conditions that led to their own journey. Familiar paradoxes would appear. The mathematics allows some of these structures under special conditions. Rotating universes, idealized cylinders, wormholes, and certain black hole solutions can contain unusual causal paths. The real universe may prevent them from forming. The required matter may be impossible to obtain. Quantum effects may destabilize the geometry. Small disturbances may grow until the path closes. A deeper law may protect the order of cause and effect. If causality could fail, one might reasonably call that a form of broken space-time. The structure would still exist, but the relationship between past and future would no longer behave in the usual way. There is currently no evidence that such paths exist in nature. Wormholes create another possible image of damage. A wormhole would connect distant regions through a shorter internal route. It is often described as a tunnel or a hole through space-time. The simplest wormholes associated with black hole solutions do not remain open long enough to cross. Traversable versions appear to require unusual energy conditions. Quantum fields can produce limited negative energy effects in certain settings, but there is no known method for collecting and arranging them to hold open a human-sized tunnel. A wormhole would not necessarily be a break. It could be a valid shape of space-time, just as a tunnel through a mountain is part of the landscape rather than a failure of geography. The important question would be whether the structure is stable and physically possible. Space-time might also break in a more fundamental sense if it is made from discrete elements. In that case, smooth geometry would be an approximation. The underlying units might form networks, loops, causal connections, or another structure. Breaking space-time could mean changing those connections until one region is no longer linked to another. The large-scale geometry would divide because the microscopic relationships producing it had been removed or rearranged. Some models connect geometry with quantum entanglement. Entanglement describes correlations between quantum systems that cannot be explained by treating them as fully independent. In certain theoretical settings, stronger entanglement corresponds to a more connected geometry. Reduce the entanglement, and the geometric connection narrows. Remove it completely in the model, and the regions separate. This is one of the closest theoretical examples of spacetime being pulled apart. It does not involve a mechanical force. It involves changing the information structure underlying geometry. There is no known machine that can perform this operation on a region of the real universe. The models are simplified and do not yet show how to disconnect the spacetime around an ordinary person, planet, or star. They do suggest that continuity may be produced by quantum relationships rather than guaranteed at the deepest level. If that is correct, force becomes a secondary concept. Force only makes sense once space, time, motion, and energy are already defined. The process that destroys space-time connectivity may need to be described without using the everyday idea of pushing or pulling. A similar issue appears if space-time is one phase of a deeper system. A material can change from solid to liquid when its temperature crosses a certain range. The solid structure disappears, but the molecules remain. Spacetime might undergo a phase transition under extreme conditions. Smooth distance and duration could disappear while more fundamental quantum degrees of freedom continue to exist. From inside the smooth phase, that transition might look like a breakdown. From the deeper viewpoint, it would be an ordinary change of state. The early universe may have experienced such a change. Black hole interiors may contain another. If so, spacetime does not break into empty nothing. It becomes a state where geometry is no longer the correct description. This leads to a useful answer. Spacetime can certainly be pushed beyond the conditions where our current classical theory works. Black holes and the early universe show that general relativity predicts singularities, and those singularities mark an incomplete description. We do not know whether spacetime itself fails there. There is no observed event in which a crack in spacetime opens and exposes an outside region. There is no measurement of separate pieces of space drifting apart. No experiment has found a maximum load beyond which geometry snaps. The phrase breaking spacetime is therefore best treated as a group of different possibilities. One possibility is extreme curvature that happens around black holes, but curvature alone is not breaking. Another is horizon formation. Horizons trap information, but the geometry at the boundary can remain smooth. A third is singularity formation. Classical relativity predicts it, but quantum gravity may remove the singularity. A fourth is the loss of causal order. Mathematics allows examples, but nature may forbid them. A fifth is the destruction of microscopic connections from which spacetime emerges. This appears in theoretical models, but it has not been experimentally demonstrated. A sixth is a phase transition into a non-geometric state. This is possible in several approaches to quantum gravity, though no single model has been confirmed. These possibilities share one feature. None can be described by a simple force value. The amount of force applied is not enough to determine the result. The location, distribution, concentration, motion, pressure, and quantum state of the energy all matter. A huge amount of mass spread across a galaxy does not form one black hole. A smaller amount compressed within a sufficiently tight region can. A powerful collision may send gravitational waves outward without creating an exposed failure. A dense collapsing core may form a horizon. An even smaller region may require quantum gravity. The outcome depends on how the energy is arranged, not only on how much exists. If someone demanded one practical answer, the closest useful statement would be this. Spacetime is expected to stop behaving as a smooth classical geometry when energy becomes concentrated near the Planck scale. It is the range where our current theories can no longer provide a complete separate description of gravity and quantum physics. The true threshold may differ. A correct theory could show that geometry survives in modified form. It could reveal a minimum length, a maximum curvature, or a transition that prevents infinities. It may show that singularities are impossible. There are theories in which curvature cannot grow without limit. Quantum effects create a maximum and cause a bounce. In those models, nature avoids breaking spacetime by changing the rules before the classical endpoint. Other theories suggest that the interior of a black hole has no smooth, empty region in the familiar sense. The quantum state fills the space where the classical interior would have been. The apparent singularity disappears because the original geometric picture was never exact. Still others suggest that the information describing a region is stored on a boundary. The interior then emerges from that information. Breaking the geometry would require changing the quantum description rather than applying a larger mechanical load. These ideas are not interchangeable. They make different claims and may lead to different observations. Future measurements of black holes, gravitational waves, early cosmic radiation, and particle behavior may eliminate many of them. More sensitive gravitational wave detectors could reveal small departures from general relativity. They could test whether black holes ring exactly as expected. They could search for additional wave patterns, unusual echoes, or evidence that horizons have unexpected structure. Observations of the early universe may show traces of quantum gravity. Patterns in ancient radiation could reveal high-energy processes that occurred when the universe was extremely young. The distribution of galaxies may preserve information about earlier fluctuations. Black hole evaporation would be especially valuable, but astronomical black holes evaporate far too slowly to observe directly. If very small black holes exist, their radiation might offer clues, though no confirmed examples have been found. Laboratory experiments continue testing whether gravity behaves normally at short distances. Precision measurements search for additional dimensions, new particles, or tiny violations of known symmetries. So far, spacetime behaves with impressive consistency. That consistency is easy to overlook. General relativity was created more than a century ago, yet it successfully predicts navigation corrections, light bending, black hole motion, and gravitational wave signals from distant mergers. The theory is incomplete at quantum scales, but it remains remarkably accurate everywhere it has been directly tested. The answer to our question is therefore less dramatic than the title first suggests, but it is more interesting. We do not know how to break spacetime with force. We do know how nature bends it. We know how stars create extreme curvature. We know how horizons form. We know how mergers send waves through the geometry. We know where classical relativity begins to produce incomplete answers. The likely breaking point is not an explosion that tears the universe open. It is a transition where space and time stop being the right concepts. Beyond that transition, there may still be a physical system. It may contain quantum information, discrete connections, extended objects, or structures not yet discovered. What disappears is the smooth stage on which ordinary events seem to happen. This is why the question remains valuable. It leads from a simple image of a torn fabric to the deepest problem in modern physics. What is space-time made from? If anything, why does it behave smoothly? How does it store information? What happens when gravity reaches the quantum scale? Until those questions are answered, we cannot say that space-time is unbreakable. We also cannot say that black holes have already broken it. The safest conclusion is that space-time appears extremely difficult to damage. It survives bending by stars, shaking by mergers, and stretching through cosmic expansion. It carries waves across the universe. It allows horizons to form without producing visible seams. Where it may fail, it hides the evidence behind a horizon or places it at scales we cannot directly reach. That may feel slightly unfair. The universe provides the question, creates the experiments, and then stores the results in locations with no return service. Even so, evidence continues to arrive. Every gravitational wave detection tests dynamic spacetime. Every image of matter near a black hole tests strong gravity. Every precise clock comparison confirms that time responds to geometry. Each observation narrows the possibilities. Perhaps a future theory will show that spacetime cannot break because it is not fundamental. Perhaps it will reveal a maximum curvature that prevents singularities. Perhaps it will show that geometry can disconnect under conditions no civilization could create. Perhaps the word spacetime will eventually be replaced by a deeper concept from which both space and time emerge. For tonight, the answer can remain careful. No known force has been shown to tear spacetime. Extreme energy can bend it, stretch it, shake it, trap light within it, and push our current theories beyond their limits. Whether reality itself breaks at those limits remains unknown. That brings us back to the place where we began. You're still in your own small region of curved spacetime, held near Earth by gravity, moving with the planet around the sun, moving with the sun through the galaxy, while clocks around you continue measuring their local paths through time. Nothing here feels stretched or unstable. The curvature is gentle. the distances remain dependable. Light crosses the room without encountering a horizon. Your tea, should you have made any, is cooling in the usual direction. If this journey through stars, black holes, gravitational waves, and the smallest scales of physics gave you something useful to think about, you can leave a like and subscribe to Sleepy Cosmic Lens. It helps this quiet collection of questions reach other listeners who may also enjoy considering the possible failure of reality shortly before falling asleep. Wherever you are listening from and whatever time your nearest clock is showing, space-time is carrying you forward without any obvious sign of strain. It has survived exploding stars, colliding black holes, and the expansion of the universe for billions of years. Whether it can truly break is still one of the questions waiting beyond the edge of what physics can currently explain.